1. Introduction to RISC-V Assembly 1.1. What is RISC-V? RISC-V is an open-source instruction set architecture (ISA) designed for computer processors. It is a type of reduced instruction set computer (RISC) architecture, which means that it uses a simplified set of instructions to perform operations. RISC-V is gaining popularity in the industry and academia due to its simplicity, flexibility, and extensibility. The RISC-V ISA was developed by the RISC-V Foundation, a nonprofit organization that promotes the adoption and standardization of the RISC-V architecture. The foundation consists of a diverse group of industry leaders, including companies like Google, NVIDIA, and Western Digital, as well as academic institutions such as the University of California, Berkeley. One of the key features of RISC-V is its modularity. The ISA is divided into different standard extensions, each providing additional functionality. These extensions include integer arithmetic and logical operations, floating point arithmetic, vector operations, and more. The modular design allows system designers to choose the specific extensions that are relevant to their applications, making RISC-V highly customizable. Another important aspect of RISC-V is its simplicity. The instruction set is designed to be easy to understand and implement, making it suitable for educational purposes and research. The simplicity of the ISA also contributes to its efficiency, as it reduces the complexity of the hardware required to execute instructions. RISC-V is also designed to be extensible, allowing users to define their own custom instructions and extensions. This flexibility enables innovation and specialization, as developers can tailor the ISA to meet the specific requirements of their applications. The extensibility of RISC-V makes it suitable for a wide range of applications, from embedded systems to high-performance computing. Furthermore, RISC-V is an open-source architecture, which means that the specifications and implementations are freely available to the public. This openness promotes collaboration and encourages the development of a vibrant ecosystem around RISC-V. It allows individuals and organizations to contribute to the improvement and evolution of the architecture, fostering innovation and community-driven development. The RISC-V ISA has gained significant traction in recent years, with many companies and organizations adopting it for various purposes. It is being used in academic research, industrial projects, and even in the development of commercial products. The availability of open-source implementations and development tools has further facilitated the adoption of RISC-V. In summary, RISC-V is an open-source instruction set architecture that offers simplicity, modularity, and extensibility. It provides a flexible and customizable platform for developing a wide range of applications. With its growing popularity and active community, RISC-V is poised to become a prominent player in the world of computer architecture. 1.2 Why learn RISC-V Assembly? RISC-V Assembly language is the low-level programming language used to write instructions for RISC-V processors. Learning RISC-V Assembly can be a valuable skill for several reasons. Understanding the inner workings of a processor. Learning RISC-V Assembly allows you to gain a deep understanding of how a processor works at the lowest level. It provides insights into the internal architecture, instruction execution, and memory management of a RISC-V processor. By learning assembly, you can comprehend the fundamental building blocks of a computer system and how they interact with each other. Efficient programming. Assembly language programming allows for fine-grained control over the hardware resources of a processor. By writing code directly in assembly, you can optimize your programs for performance and efficiency. Assembly programs can be highly optimized, resulting in faster execution times and reduced memory usage. This level of control is especially important in embedded systems and real-time applications where every cycle and byte count. Debugging and troubleshooting. Understanding assembly language can be immensely helpful when it comes to debugging and troubleshooting programs. Assembly code provides a low-level view of the program execution, allowing you to analyze the state of the processor and memory at each step. By understanding assembly, you can identify and fix issues such as memory leaks, incorrect register usage, and logic errors that may not be apparent at higher-level languages. Portability and compatibility. RISC-V is an open-source instruction set architecture, which means that it can be implemented on various hardware platforms. By learning RISC-V assembly, you gain the ability to write code that can run on any RISC-V-compatible processor, regardless of the underlying hardware. This portability allows you to develop software that can be easily migrated across different RISC-V platforms, making your skills highly transferable. Low-level system programming. Assembly language is often used for low-level system programming tasks such as writing device drivers, operating systems, and firmware. By learning RISC-V assembly, you can gain the skills required to work on these critical components of a computer system. This knowledge opens up opportunities to work on embedded systems, IoT devices, and other specialized hardware platforms. Understanding compiler output. Learning assembly language can help you understand the output generated by compilers when you write code in higher-level languages such as C or C++. By understanding assembly, you can analyze the generated code, identify potential optimizations, and gain insights into how the compiler translates high-level code into low-level instructions. Academic and research purposes. RISC-V is gaining popularity in academic and research communities due to its open-source nature and simplicity. By learning RISC-V assembly, you can actively participate in research projects, contribute to the development of new tools and libraries, and explore novel ideas in computer architecture and system design. In conclusion, learning RISC-V assembly language provides a solid foundation in computer architecture, enables efficient programming, enhances debugging and troubleshooting skills, and opens up opportunities in low-level system programming. Whether you are interested in understanding the inner workings of a processor, optimizing code for performance, or working on embedded systems, learning RISC-V assembly is a valuable skill that can benefit you in various ways. 1.3 Setting up the RISC-V development environment. Setting up the RISC-V development environment is an essential step before you can start writing and running RISC-V assembly programs. In this section, we will guide you through the process of setting up the necessary tools and software to begin your journey into RISC-V assembly programming. Installing the RISC-V toolchain. The first step in setting up the RISC-V development environment is to install the RISC-V toolchain. The toolchain consists of a set of software tools that are required to compile and run RISC-V assembly programs. These tools include the RISC-V assembler, linker, and simulator. There are several options available for installing the RISC-V toolchain, depending on your operating system. One popular option is to use the new toolchain for RISC-V, which provides a complete set of tools for RISC-V development. To install the new toolchain, you can follow these steps. Visit the official RISC-V website and navigate to the Software section. Look for the new toolchain for RISC-V and download the appropriate version for your operating system. Once the download is complete, extract the contents of the archive to a directory of your choice. Add the directory containing the toolchain binaries to your system's path environment variable. This will allow you to run the RISC-V tools from any location in your terminal. Choosing an integrated development environment (IDE). While it is possible to write and compile RISC-V assembly programs using a simple text editor and command line tools, using an integrated development environment (IDE) can greatly enhance your productivity and make the development process more efficient. There are several IDEs available that support RISC-V assembly programming. Some popular options include Visual Studio Code, a lightweight and extensible IDE that provides excellent support for RISC-V assembly programming through various extensions. Eclipse, a powerful and feature-rich IDE that offers comprehensive support for RISC-V development, including debugging capabilities. Atom, a highly customizable and hackable text editor that can be transformed into a full-fledged IDE for RISC-V assembly programming using the appropriate extensions. Choose an IDE that suits your preferences and install it on your system. Once installed, configure the IDE to recognize RISC-V assembly files and provide syntax highlighting and code completion features. Setting up a simulator. To test and run your RISC-V assembly programs, you will need a simulator that emulates the behavior of a RISC-V processor. Simulators allow you to execute your assembly code and observe the results without the need for actual hardware. One popular simulator for RISC-V is Spike, which is part of the RISC-V new toolchain. Spike provides a functional simulation of a RISC-V processor and allows you to run RISC-V assembly programs on your computer. To set up Spike, follow these steps. Ensure that you have installed the RISC-V new toolchain as described earlier. Open a terminal and navigate to the directory where you extracted the toolchain. Run the following command to start Spike, Spike-H. This will launch a Spike simulator and display the available options and commands. You can use Spike to load and execute your RISC-V assembly programs, as well as observe the program's output and behavior. Testing the development environment. Once you have installed the necessary tools and software, it is a good idea to test your RISC-V development environment to ensure everything is set up correctly. You can do this by writing a simple, Hello World, program in RISC-V assembly and running it using the simulator. Create a new file in your IDE and save it with a S extension, e.g., hello, S. In this file, write the following RISC-V assembly code. Section, data MSG, ASCIZ, hello, world. N. Section, text, global _start_start. Hash print the message la A0, MSG li A1, 14 li A7, 64 equal. Hash exit the program li A7, 93 li A0, 0 equal. Save the file and compile it using the RISC-V assembler. Open a terminal and navigate to the directory where you saved the file. Run the following command. RISC-V64 unknown elf is oh hello, s. This will generate an object file, hello, oh, from your assembly code. Next, link the object file using the RISC-V linker. RISC-V64 unknown elf LDO hello, oh. Finally, run the program using the Spike simulator. Spike PK hello. If everything is set up correctly, you should see the message, hello, world, printed in the terminal. Congratulations! You have successfully set up your RISC-V development environment and tested it by running a simple assembly program. You are now ready to dive deeper into RISC-V assembly programming and explore the various instructions and techniques available to you. 1.4 Hello World in RISC-V Assembly. In this section, we will explore how to write a simple, Hello World program in RISC-V assembly language. This program will serve as a basic introduction to the syntax and structure of RISC-V assembly code. To begin, let's understand the basic structure of a RISC-V assembly program. A RISC-V program consists of a series of instructions that are executed sequentially by the processor. Each instruction performs a specific operation, such as loading data from memory, performing arithmetic calculations, or branching to a different part of the program. The Hello World program is a traditional first program in many programming languages. It simply prints the message, Hello World, to the console. In RISC-V assembly, we can achieve this by using the system call instruction to output the message to the console. Here is the RISC-V assembly code for the Hello World program. Data. Message, ASCIIZ, Hello World. Text. Global main. Main. Hash print the message li A0, 1 li A1, message li A2, 13 li A7, 64 equal. Hash exit the program li A7, 93 li A0, 0 equal. Let's break down the code step by step. The data section is used to declare data variables. In this case, we define a null terminated string called message which contains the text, Hello World. The text section is where the actual instructions of the program are written. The global main directive declares the main function as the entry point of the program. Inside the main function, we perform the following steps. Load the system call number for writing to the console into register A7, 64 in this case. Load the address of the message string into register A1. Load the length of the message string, 13 characters, into register A2. Load the system call number for making a system call into register A7, 64 in this case. Execute the eCall instruction to make the system call and print the message to the console. After printing the message, we want to exit the program. To do this, we perform the following steps. Load the system call number for program exit into register A7, 93 in this case. Load the exit status code, 0 in this case, into register A0. Execute the eCall instruction to make the system call and exit the program. To run this program, you will need a RISC-V simulator or an actual RISC-V processor. You can assemble and run the program using a RISC-V toolchain, such as the new compiler collection GCC for RISC-V. Once you have set up the RISC-V development environment, save the Hello World program in a file with a S extension, e.g., hello s. Then, use the following command to assemble and run the program. $RISC-V 64 unknown elf GCCO hello $spike pk hello. The first command compiles the assembly code into a binary executable called hello. The second command runs the program using the Spike simulator. When you run the program, you should see the message, Hello World, printed to the console. Congratulations! You have successfully written and executed your first RISC-V assembly program. This simple program serves as a foundation for understanding the basic syntax and structure of RISC-V assembly code. In the following chapters, we will explore more advanced topics and learn how to write more complex programs in RISC-V assembly. 2. RISC-V instruction set architecture. 2.1 Overview of RISC-V ISA. The RISC-V instruction set architecture ISA is an open-source, modular, and extensible instruction set architecture designed for a wide range of computing devices. It is a reduced instruction set computer RISC architecture, which means it uses a small set of simple instructions that can be executed in a single clock cycle. This simplicity allows for efficient and fast execution of instructions, making RISC-V an attractive choice for various applications. Key features of RISC-V ISA. The RISC-V ISA is designed with several key features that make it versatile and adaptable to different computing environments. Modularity. The RISC-V ISA is modular, meaning it can be customized and extended to meet the specific requirements of different applications. This modularity allows for the inclusion of optional instruction sets, making it suitable for a wide range of devices, from embedded systems to high-performance servers. Scalability. The RISC-V ISA is scalable, supporting both 32-bit and 64-bit address spaces. This scalability enables RISC-V to be used in a variety of systems, from resource-constrained devices to large-scale servers. Simplicity. The RISC-V ISA follows a simple and elegant design philosophy, with a small number of core instructions that are easy to understand and implement. This simplicity makes it easier to develop compilers, debuggers, and other software tools for RISC-V. Extensibility. The RISC-V ISA allows for the addition of custom instructions and extensions without breaking compatibility with existing software. This extensibility enables developers to tailor the instruction set to their specific needs, improving performance and energy efficiency. Open source. One of the most significant advantages of RISC-V is its open source nature. The ISA specifications are freely available, allowing anyone to study, modify, and implement the architecture without any licensing restrictions. This openness fosters collaboration and innovation within the RISC-V community. Instruction formats. The RISC-V ISA defines several instruction formats that determine how instructions are encoded and interpreted by the processor. These formats include R-type. The R-type format is used for arithmetic and logical instructions that operate on two source registers and store the result in a destination register. This format is commonly used for operations such as addition, subtraction, bitwise AND, and bitwise OR. I-type. The I-type format is used for instructions that operate on an immediate value in a source register, storing the result in a destination register. This format is commonly used for load and store instructions, as well as arithmetic and logical operations with immediate values. S-type. The S-type format is used for store instructions that store a value from a source register into memory. This format includes an immediate offset that specifies the memory address. B-type. The B-type format is used for branch instructions that perform conditional jumps based on a comparison between two source registers. This format includes an immediate offset that determines the target address. U-type. The U-type format is used for instructions that load an immediate value into a destination register. This format is commonly used for initializing variables or setting up memory addresses. J-type. The J-type format is used for jump instructions that perform unconditional jumps to a target address. This format includes an immediate offset that determines the target address. Register file. The RISC-V ISA includes a set of general-purpose registers that can be used to store data and perform calculations. The number of registers and their sizes depend on the specific implementation of the RISC-V architecture. However, the standard RISC-V specification defines 32 general-purpose registers, labeled from X0 to X31. Some of these registers have special purposes, such as X0, which is hardwired to 0 and cannot be modified. Other registers, like X1, are reserved for specific purposes, such as the return address in function calls. The general-purpose registers can be used to store data, perform arithmetic and logical operations, and hold memory addresses for load and store instructions. They provide a fast and efficient way to manipulate data within the processor. Conclusion. The RISC-V ISA is a versatile and open-source instruction set architecture that offers modularity, scalability, simplicity, extensibility, and compatibility. Its simplicity and modularity make it an excellent choice for learning assembly language programming and understanding the fundamentals of computer architecture. In the next section, we will explore the RISC-V registers in more detail, which play a crucial role in executing instructions and storing data. 2.2 RISC-V registers. In RISC-V assembly language programming, registers play a crucial role in storing and manipulating data. Registers are small, high-speed storage locations within the processor that can hold data temporarily during program execution. RISC-V architecture provides a set of 32 general-purpose registers, each of which is 32 bits wide. These registers are labeled from X0 to X31, where X0 is a special register that always holds the value 0. The RISC-V registers can be broadly categorized into three types: integer registers, floating point registers, and control registers. In this section, we will focus on the integer registers, as they are the most commonly used registers in RISC-V assembly programming. Integer registers. The integer registers in RISC-V are denoted by the prefix X, followed by a number from 0 to 31. These registers are 32 bits wide and can store both data and addresses. The registers X1 to X31 are general-purpose registers that can be used for any purpose in the program. However, some registers have special purposes and conventions associated with them. 0 register X0. The 0 register, X0, is a special-purpose register that always holds the value 0. It cannot be written to or modified by any instruction. It is often used as a source register when an instruction requires a 0 value. Return address register, X1. The return address register, X1, is used to store the return address of a function call. When a function is called, the address of the instruction following the function call is stored in X1. This allows the program to return to the correct location after the function call is completed. Argument and temporary registers, X2, X7. The registers X2 to X7 are commonly used as argument and temporary registers. They can be used to pass arguments to functions and store temporary values during program execution. However, it is important to note that these registers are not preserved across function calls, meaning their values may be modified by function calls. Saved registers X8, X9. The registers X8 and X9, also known as S0 and S1, are saved registers. These registers are preserved across function calls, meaning their values are not modified by function calls. They can be used to store important values that need to be preserved across function calls. Global pointer X10. The global pointer register, X10, is used to point to the base address of the global data segment. It is often used to access global variables and data structures. Stack pointer X2. The stack pointer register, X2, is used to point to the top of the stack. The stack is a region of memory used for storing local variables and function call information. The stack pointer is automatically updated by the system when pushing or popping values onto or from the stack. Frame pointer X8. The frame pointer register, X8, is used to point to the base address of the current stack frame. It is often used to access local variables and function parameters within a function. Return value registers X10, X11. The registers X10 and X11, also known as A0 and A1, are used to store the return values of a function. When a function returns a value, it is stored in one of these registers. Temporary registers X12, X17. The registers X12 to X17 are commonly used as temporary registers. They can be used to store intermediate values during program execution. However, it is important to note that these registers are not preserved across function calls. Saved registers X18, X27. The registers X18 to X27, also known as S2 to S11, are saved registers. Similar to X8 and X9, these registers are preserved across function calls and can be used to store important values that need to be preserved. Return address register X28. The return address register, X28, is used to store the return address of a function call. It is similar to X1 but can be used as an additional return address register if needed. Stack pointer X29. The stack pointer register, X29, is used to point to the top of the stack. It is similar to X2 but can be used as an additional stack pointer if needed. Global pointer X30. The global pointer register, X30, is similar to X10 and can be used as an additional global pointer if needed. Program counter X31. The program counter register, X31, holds the address of the next instruction to be executed. It is automatically updated by the system as the program progresses. Conclusion. Understanding the different registers in RISC-V assembly language programming is essential for writing efficient and effective code. The integer registers provide a means to store and manipulate data during program execution. By utilizing the various registers effectively, programmers can optimize their code and achieve better performance. In the next section, we will explore the different instruction formats used in RISC-V assembly language programming. 2.3 RISC-V instruction formats. In order to understand how instructions are encoded and executed in RISC-V assembly language, it is important to have a clear understanding of the different instruction formats used in the RISC-V instruction set architecture (ISA). The RISC-V ISA defines three basic instruction formats: R-type, I-type, and S-type. Each format is designed to accommodate different types of instructions and operands. R-type format. The R-type format is used for instructions that perform operations on registers. These instructions typically involve arithmetic, logical, and shift operations. The R-type format consists of a 32-bit instruction word divided into several fields. The opcode field, 6 bits, specifies the operation to be performed. The ROAD field, 5 bits, specifies the destination register where the result of the operation will be stored. The RS1 field, 5 bits, specifies the first source register. The RS2 field, 5 bits, specifies the second source register. The funct3 field, 3 bits, further specifies the operation within the opcode category. The funct7 field, 7 bits, provides additional information for certain instructions. An example of an R-type instruction is a add instruction, which adds the values of two registers and stores the result in a destination register. The opcode for the add instruction is 01100011, and the funct3 field for addition is 000. The funct7 field is not used for addition. The ROAD, 1 rupee, and RS2 fields specify the registers involved in the operation. I-type format. The I-type format is used for instructions that involve immediate values, such as immediate arithmetic, logical, and load instructions. The I-type format also consists of a 32-bit instruction word divided into several fields. The opcode field, 6 bits, specifies the operation to be performed. The ROAD field, 5 bits, specifies the destination register. The RS1 field, 5 bits, specifies the source register. The IMM field, 12 bits, specifies the immediate value. The I-type format allows for immediate values to be directly encoded within the instruction itself, which eliminates the need to load immediate values from memory. This makes I-type instructions more efficient for operations that involve immediate values. An example of an I-type instruction is the ADD instruction, which adds an immediate value to the value of a register and stores the result in a destination register. The opcode for the ADD instruction is 00100011. The ROAD and RS1 fields specify the registers involved in the operation, and the IMM field specifies the immediate value to be added. S-type format. The S-type format is used for instructions that store values to memory. These instructions typically involve store operations. The S-type format also consists of a 32-bit instruction word divided into several fields. The opcode field, 6 bits, specifies the operation to be performed. The RS1 field, 5 bits, specifies the source register. The RS2 field, 5 bits, specifies the second source register. The IMM field, 12 bits, specifies the immediate value. The S-type format allows for storing values to memory by specifying both the source register and the immediate value within the instruction itself. This eliminates the need for separate load and store instructions, making the S-type format more efficient for memory operations. An example of an S-type instruction is the SW instruction, which stores the value of a register to memory. The opcode for the SW instruction is 010011. The Rs1 and 2 rupees fields specify the registers involved in the operation, and the IMM field specifies the immediate value used as an offset for the memory address. Other formats. In addition to the R-type, I-type, and S-type formats, the RISC-V ISA also includes formats for branch, jump, and system instructions. These formats are designed to accommodate instructions that control program flow, handle interrupts and exceptions, and interact with the operating system. The branch instructions use the B-type format, which includes fields for the opcode, 1 rupee, 2 rupees, and an immediate value for the branch offset. The jump instructions use the J-type format, which includes fields for the opcode, road, and an immediate value for the jump target address. The system instructions use the U-type format, which includes fields for the opcode, road, and an immediate value for system calls and other privileged operations. Understanding the different instruction formats in the RISC-V ISA is crucial for writing efficient and correct assembly code. By knowing how instructions are encoded and how operands are specified, programmers can effectively utilize the capabilities of the RISC-V architecture and optimize their code for performance. 2.4 RISC-V addressing modes. In RISC-V assembly language, addressing modes determine how operands are accessed and specified in memory instructions. An addressing mode specifies the location of the data to be operated on by an instruction. RISC-V supports several addressing modes, each with its own advantages and use cases. Understanding and utilizing these addressing modes is crucial for efficient and effective programming in RISC-V assembly. Immediate addressing mode. Immediate addressing mode allows the use of immediate values directly in instructions. In this mode, the operand is a constant value that is included in the instruction itself. Immediate values are typically used for small constants or immediate data. For example, the ADDI instruction adds an immediate value to a register. The immediate value is specified directly in the instruction, allowing for quick and easy manipulation of data. Register addressing mode. Register addressing mode involves using registers to specify the operands of an instruction. In this mode, the operands are stored in registers, and the instruction operates on the values stored in those registers. RISC-V has a total of 32 general-purpose registers, labeled X0 to X31. Register addressing mode is commonly used for arithmetic and logical operations, as well as for storing and retrieving data. Base or displacement addressing mode. Base or displacement addressing mode involves using a base register and an offset to access memory. The base register holds the starting address, and the offset specifies the displacement from the base address. This addressing mode is useful when working with arrays or data structures stored in memory. By using a base register and an offset, you can easily access elements of an array or navigate through a data structure. PC relative addressing mode. PC relative addressing mode allows for addressing memory locations relative to the program counter PC. The PC holds the address of the current instruction being executed. This addressing mode is commonly used for branching and jumping instructions. By specifying an offset relative to the PC, you can easily perform conditional jumps or branches to different parts of the program. Absolute addressing mode. Absolute addressing mode involves directly specifying the memory address of the operand. This addressing mode is useful when you need to access a specific memory location, such as a memory map device or a specific data structure. However, it is important to note that using absolute addressing can make your code less portable, as the memory layout may vary between different systems. Indirect addressing mode. Indirect addressing mode involves using a register to hold the memory address of the operand. Instead of directly specifying the memory address, you specify a register that holds the address. This addressing mode is useful when working with pointers or when the memory address is determined dynamically during program execution. Base with index addressing mode. Base with index addressing mode combines the base or displacement addressing mode with an index register. In this mode, the base register holds the starting address, and the index register holds the offset or index. This addressing mode is commonly used in array operations, where the base register points to the start of the array, and the index register is used to access specific elements within the array. Summary. RISC-V assembly language provides several addressing modes to facilitate efficient and flexible programming. Each addressing mode has its own advantages and use cases, and understanding when and how to use each mode is essential for writing optimized and effective code. By leveraging the different addressing modes available in RISC-V, you can manipulate data, access memory, and control program flow with precision and efficiency. 3. Data manipulation instructions. 3.1 Load and store instructions. In RISC-V assembly language, load and store instructions are used to manipulate data in memory. These instructions allow the processor to access data from memory and store data back into memory. Understanding how to use load and store instructions is essential for working with data in RISC-V assembly programs. Load instructions. Load instructions are used to retrieve data from memory and store it in a register. The syntax for load instructions is as follows. LW load, offset 1 rupee. In this syntax, LW is the load word instruction, load is the destination register where the data will be stored, offset is the offset from the base address stored in register 1 rupee, and RS1 is the base register that holds the memory address. For example, let's say we have an array of integers stored in memory starting at address 0x1000. We want to load the value at index 3 of the array into register x5. We can use the following load instruction. LWX5, 12x0. In this example, x5 is the destination register, 12 is the offset from the base address x0, and x0 is the base register that holds the base address 0x1000. The value at index 3 of the array will be loaded into x5. Store instructions. Store instructions are used to store data from a register into memory. The syntax for store instructions is as follows. SW 2 rupees, offset 1 rupee. In this syntax, SW is the store word instruction, 2 rupees is the source register that holds the data to be stored, offset is the offset from the base address stored in register 1 rupee, and RS1 is the base register that holds the memory address. Continuing with the previous example, if we want to store a value in register x6 into index 5 of the array, we can use the following store instruction. SWX6, 20x0. In this example, x6 is the source register that holds the data to be stored, 20 is the offset from the base address x0, and x0 is the base register that holds the base address 0x1000. The value in x6 will be stored at index 5 of the array. Addressing modes. RISC-V supports different addressing modes for load and store instructions. The most common addressing modes are immediate offset. The offset is a constant value specified in the instruction itself. For example, LWX1, 4x0 loads the value at address x0 plus 4 into x1. Register offset. The offset is stored in a register. For example, LWX1, x2, x0 loads the value at address x0 plus x2 into x1. Base plus index. The offset is the sum of a base register and an index register. For example, LWX1, x2, x3 loads the value at address x3 plus x2 into x1. Scaled index. The offset is the sum of a base register, an index register, and a scale factor. For example, LWX1, 4 x2, x3 loads the value at address x2 plus 4 asterisk x3 into x1. These addressing modes provide flexibility in accessing data from memory and allow for efficient manipulation of arrays and data structures. Memory alignment. When working with load and store instructions, it is important to consider memory alignment. RISC-V requires that memory accesses are aligned to their data size. For example, a word 32 bits must be aligned on a 4-byte boundary. If a memory access is not aligned, it may result in a misaligned memory access exception. To ensure proper alignment, it is recommended to align data structures and arrays to the appropriate boundaries. This can be achieved by using the align directive in assembly code. Summary. Load and store instructions are fundamental in RISC-V assembly language for accessing and manipulating data in memory. Load instructions retrieve data from memory and store it in registers, while store instructions store data from registers back into memory. Understanding the different addressing modes and memory alignment requirements is crucial for efficient and correct data manipulation in RISC-V assembly programs. 3.2 Arithmetic instructions. Arithmetic instructions are an essential part of any programming language, including assembly languages. In RISC-V assembly, arithmetic instructions allow you to perform basic mathematical operations on data stored in registers. These operations include addition, subtraction, multiplication, and division. Addition. The addition operation in RISC-V assembly is performed using the add instruction. This instruction takes 3 operands, a destination register, and 2 source registers. The add instruction adds the values of the 2 source registers and stores the result in the destination register. For example, the following code snippet adds the values in registers x1 and x2 and stores the result in register x3. Add x3, x1, x2 subtraction. Subtraction in RISC-V assembly is performed using the sub instruction. Similar to the add instruction, the sub instruction takes 3 operands, a destination register, and 2 source registers. The sub instruction subtracts the value of the second source register from the value of the first source register and stores the result in the destination register. Here's an example. Sub x3, x1, x2 multiplication. The multiplication operation in RISC-V assembly is performed using the mul instruction. Like the previous instructions, the mul instruction also takes 3 operands, a destination register, and 2 source registers. The mul instruction multiplies the values of the 2 source registers and stores the result in the destination register. Here's an example. Mul x3, x1, x2 division. Division in RISC-V assembly is performed using the div instruction. The div instruction takes 3 operands, a destination register, and 2 source registers. The div instruction divides the value of the first source register by the value of the second source register and stores the quotient in the destination register. Here's an example. Div x3, x1, x2 remainder. In addition to division, the div instruction also calculates the remainder of the division operation. The remainder is stored in a separate register called the remainder register rem. To calculate the remainder, you need to use the rem instruction. Here's an example. Rem x4, x1, x2. Immediate arithmetic instructions. In addition to the arithmetic instructions mentioned above, RISC-V Assembly also provides immediate arithmetic instructions. These instructions allow you to perform arithmetic operations with immediate values, which are constants embedded directly in the instruction. Immediate arithmetic instructions are useful when you need to perform arithmetic operations with constants without loading them into registers first. The immediate arithmetic instructions follow a similar syntax to their non-immediate counterparts. For example, the ADDI instruction adds an immediate value to a register and stores the result in another register. Here's an example. ADDI x3, x1, 10. This instruction adds the immediate value 10 to the value in register x1 and stores the result in register x3. Other immediate arithmetic instructions include SUBI, MULI, and DIVI, which perform subtraction, multiplication, and division with immediate values, respectively. Summary. Arithmetic instructions are fundamental in RISC-V assembly programming. They allow you to perform basic mathematical operations such as addition, subtraction, multiplication, and division. Additionally, RISC-V Assembly provides immediate arithmetic instructions for performing arithmetic operations with immediate values. Understanding and utilizing these instructions will enable you to manipulate data effectively in your assembly programs. 3.3 Logical Instructions. Logical instructions in RISC-V assembly language are used to perform bitwise operations on data. These operations manipulate individual bits within a register or memory location. Logical instructions are essential for tasks such as data masking, bit manipulation, and Boolean operations. In this section, we will explore the different logical instructions available in RISC-V and learn how to use them effectively in assembly programming. AND instruction. The AND instruction performs a bitwise AND operation between two operands and stores the result in a destination register. The syntax for the AND instruction is as follows. AND ROAD, 1 rupee, 2 rupees. Here, ROAD is the destination register, 1 rupee is the first source register, and RS2 is the second source register. The AND instruction performs a logical AND operation between the corresponding bits of 1 rupee and RS2 and stores the result in ROAD. OR instruction. The OR instruction performs a bitwise OR operation between two operands and stores the result in a destination register. The syntax for the OR instruction is as follows. OR ROAD, 1 rupee, 2 rupees. Similar to the AND instruction, ROAD is the destination register, 1 rupee is the first source register, and RS2 is the second source register. The OR instruction performs a logical OR operation between the corresponding bits of 1 rupee and RS2 and stores the result in ROAD. XOR instruction. The XOR instruction performs a bitwise XOR, exclusive OR, operation between two operands and stores the result in a destination register. The syntax for the XOR instruction is as follows. XOR ROAD, 1 rupee, 2 rupees. Again, ROAD is the destination register, 1 rupee is the first source register, and RS2 is the second source register. The XOR instruction performs a logical XOR operation between the corresponding bits of 1 rupee and RS2 and stores the result in ROAD. NOT instruction. The NOT instruction performs a bitwise NOT operation on a single operand and stores the result in a destination register. The syntax for the NOT instruction is as follows. NOT ROAD, 1 rupee. Here, ROAD is the destination register, and RS1 is the source register. The NOT instruction performs a logical NOT operation on each bit of 1 rupee and stores the result in ROAD. Logical shift instructions. RISC-V assembly language provides logical shift instructions to shift the bits of a register left or right. These instructions are useful for tasks such as multiplication or division by powers of 2. The logical shift instructions include SLL, shift left logical, shifts the bits of a register to the left by a specified number of positions. SRL, shift right logical, shifts the bits of a register to the right by a specified number of positions. SRA, shift right arithmetic, shifts the bits of a register to the right by a specified number of positions, while preserving the sign bit. The syntax for the logical shift instructions is as follows. SLL ROAD, 1 rupee, shamt SRL ROAD, 1 rupee, shamt SRA ROAD, 1 rupee, shamt. Here, ROAD is the destination register, 1 rupee is the source register, and shamt is the shift amount. The shift amount specifies the number of positions to shift the bits. Bit manipulation techniques. Logical instructions are often used for bit manipulation tasks in assembly programming. Bit manipulation involves setting, clearing, or toggling specific bits within a register. Here are some common bit manipulation techniques using logical instructions. Setting a bit. To set a specific bit within a register, you can use the OR instruction with a mask that has only that bit set to 1. Clearing a bit. To clear a specific bit within a register, you can use the AND instruction with a mask that has only that bit set to 0. Toggling a bit. To toggle a specific bit within a register, change 1 to 0 or 0 to 1, you can use the XOR instruction with a mask that has only that bit set to 1. These techniques are useful for tasks such as manipulating control bits, flags, or individual bits within a data structure. Boolean operations. Logical instructions can also be used to perform Boolean operations, such as AND, OR, and XOR, on binary values. These operations are commonly used in conditional statements and Boolean logic. By combining logical instructions with conditional branch instructions, complex Boolean expressions can be evaluated efficiently in assembly language. In conclusion, logical instructions in RISC-V assembly language provide powerful tools for manipulating bits, performing Boolean operations, and implementing bit-level algorithms. By understanding and utilizing these instructions effectively, you can write efficient and optimized assembly programs for a wide range of applications. 3.4 Shift and Rotate Instructions. Shift and rotate instructions are essential in RISC-V assembly language programming for manipulating data at the bit level. These instructions allow you to shift or rotate the bits of a register operand to the left or right. They are particularly useful for tasks such as multiplying or dividing by powers of 2, extracting specific bits, or implementing bitwise operations. Shift instructions. Shift instructions move the bits of a register operand left or right by a specified number of positions. The two types of shift instructions in RISC-V are logical shifts and arithmetic shifts. Logical shifts. Logical shifts, also known as unsigned shifts, treat the operand as an unsigned value and fill the vacated bits with zeros. There are two logical shift instructions in RISC-V. SLL Road, 1 rupee, 2 rupees, shift left logical. The bits in register RS1 are shifted left by the number of positions specified in the least significant 5 bits of register 2 rupees. The result is stored in register road. SRL Road, 1 rupee, 2 rupees, shift right logical. The bits in register RS1 are shifted right by the number of positions specified in the least significant 5 bits of register 2 rupees. The result is stored in register road. Here's an example that demonstrates the usage of logical shift instructions. Hash shift left logical. SLL X1, X2, 3 hash shift the bits in X2 left by 3 positions and store the result in X1. Hash shift right logical. SRL X3, X4, 5 hash shift the bits in X4 right by 5 positions and store the result in X3 arithmetic shifts. Arithmetic shifts, also known as signed shifts, treat the operand as a signed value and fill the vacated bits with the sign bit. There are two arithmetic shift instructions in RISC-V. SRA Road, 1 rupee, 2 rupees, shift right arithmetic. The bits in register RS1 are shifted right by the number of positions specified in the least significant 5 bits of register 2 rupees. The sign bit is replicated to fill the vacated bits. The result is stored in register road. SLL Road, 1 rupee, 2 rupees, shift left logical. The bits in register RS1 are shifted left by the number of positions specified in the least significant 5 bits of register 2 rupees. The result is stored in register road. Here's an example that demonstrates the usage of arithmetic shift instructions. Hash shift right arithmetic. SRA X1, X2, 4 hash shift the bits in X2 right by 4 positions and store the result in X1. Hash shift left logical. SLL X3, X4, 2 hash shift the bits in X4 left by 2 positions and store the result in X3 rotate instructions. Rotate instructions circularly shift the bits of a register operand to the left or right, wrapping the shifted bits around to the opposite end. RISC-V provides 2 rotate instructions. RR Road, 1 rupee, 2 rupees, rotate right. The bits in register RS1 are rotated right by the number of positions specified in the least significant 5 bits of register 2 rupees. The result is stored in register road. RAL Road, 1 rupee, 2 rupees, rotate left. The bits in register RS1 are rotated left by the number of positions specified in the least significant 5 bits of register 2 rupees. The result is stored in register road. Here's an example that demonstrates the usage of rotate instructions. Hash rotate right. RR X1, X2, 6 hash rotate the bits in X2 right by 6 positions and store the result in X1. Hash rotate left. RAL X3, X4, 7 hash rotate the bits in X4 left by 7 positions and store the result in X3 rotate instructions are particularly useful when you need to implement circular buffers, circular queues, or bitwise operations that require wrapping of bits. Summary. Shift and rotate instructions are powerful tools for manipulating data at the bit level in RISC-V assembly language programming. Logical shifts allow you to shift bits left or right, filling the vacated bits with zeros. Arithmetic shifts, on the other hand, fill the vacated bits with the sign bit. Rotate instructions circularly shift the bits, wrapping them around to the opposite end. These instructions are essential for tasks such as multiplying or dividing by powers of 2, extracting specific bits, or implementing bitwise operations. 3.5 Comparison instructions. Comparison instructions are an essential part of any programming language, including assembly languages. In RISC-V assembly, comparison instructions allow us to compare two values and perform conditional operations based on the result of the comparison. These instructions are crucial for making decisions and controlling the flow of execution in our programs. 3.5.1 Comparing registers. RISC-V provides several comparison instructions that allow us to compare the values stored in registers. These instructions include SLT set less than. This instruction sets the destination register to 1 if the source register RS1 is less than the source register 2 rupees, and 0 otherwise. SLTU set less than unsigned, similar to SLT, but performs an unsigned comparison. Sergeant set greater than. This instruction sets the destination register to 1 if the source register RS1 is greater than the source register 2 rupees, and 0 otherwise. SGTU set greater than unsigned, similar to Sergeant, but performs an unsigned comparison. Seek set equal. This instruction sets the destination register to 1 if the source register RS1 is equal to the source register 2 rupees, and 0 otherwise. SNEAT set not equal. This instruction sets the destination register to 1 if the source register RS1 is not equal to the source register 2 rupees, and 0 otherwise. These comparison instructions are used in combination with conditional branch instructions to control the flow of execution based on the result of the comparison. 3.5.2 Conditional branch instructions. Conditional branch instructions allow us to perform a branch jump to a different location in the program based on a condition. In RISC-V assembly, conditional branch instructions are typically used in conjunction with comparison instructions to make decisions. The conditional branch instructions in RISC-V include BEQ branch if equal. This instruction branches to the target address if the source register RS1 is equal to the source register 2 rupees. BNE branch if not equal. This instruction branches to the target address if the source register RS1 is not equal to the source register 2 rupees. BLT branch if less than. This instruction branches to the target address if the source register RS1 is less than the source register 2 rupees. BLTU branch if less than unsigned, similar to BLT, but performs an unsigned comparison. BGE branch if greater than or equal. This instruction branches to the target address if the source register RS1 is greater than or equal to the source register 2 rupees. BGEU branch if greater than or equal unsigned, similar to BGE, but performs an unsigned comparison. Conditional branch instructions are often used in control flow structures such as if-else statements and loops. By combining comparison instructions with conditional branch instructions, we can create complex decision-making logic in our assembly programs. 3.5.3 Example usage. Let's look at an example to understand how comparison and conditional branch instructions work together. Consider the following RISC-V assembly code. ADDI x1, x0, 5 hash load 5 into register x1 ADDI x2, x0, 10 hash load 10 into register x2. SLT x3, x1, x2 hash compare x1 and x2 using SLT BEQ x3, x0, equal hash branch to equal if x3 is 0. Hash if x3 is not 0, execute the following instructions ADDI x4, x0, 1 hash load 1 into register x4 add x5, x1, x4 hash add x1 and x4, store result in x5j end hash jump to end. Equal. ADDI x5, x0, 0 hash load 0 into register x5. End. Hash rest of the program. In this example, we compare the values stored in registers x1 and x2 using the SLT instruction. If x1 is less than x2, the result of the comparison x3 will be 1, and we branch to the equal label. If x1 is not less than x2, the result of the comparison will be 0, and we continue executing the instructions after the BEQ instruction. Inside the equal label, we load 0 into register x5. After that, we jump to the end label using the J instruction. The end label marks the end of the program, and the execution continues from there. This example demonstrates how comparison and conditional branch instructions can be used to create decision-making logic in RISC-V assembly programs. Conclusion. Comparison instructions and conditional branch instructions are fundamental to controlling the flow of execution in RISC-V assembly programs. By comparing values and making decisions based on the results, we can create complex logic and implement control flow structures. Understanding these instructions is crucial for writing efficient and effective assembly programs. 3.6 Branch and jump instructions. Branch and jump instructions are essential for controlling the flow of execution in an RISC-V assembly program. These instructions allow the program to make decisions, loop through code, and call subroutines. In this section, we will explore the different branch and jump instructions available in RISC-V and learn how to use them effectively. Branch instructions. Branch instructions are used to conditionally change the flow of execution based on the result of a comparison. They allow the program to make decisions and execute different sections of code depending on the outcome. RISC-V provides several branch instructions, including BEQ, BNE, BLT, BGE, BLTU, and BGEU. The BEQ instruction branches to a target address if two registers are equal. For example, the following code snippet demonstrates the usage of the BEQ instruction. BEQ x1, x2, label. In this example, if the values in registers x1 and x2 are equal, the program will branch to the label address. Otherwise, it will continue executing the next instruction. Similarly, the BNE instruction branches if two registers are not equal. The BLT instruction branches if the first register is less than the second register, while BGE branches if the first register is greater than or equal to the second register. The BLTU and BGEU instructions are similar to BLT and BGE, but they treat the registers as unsigned integers. Jump instructions. Jump instructions allow the program to transfer control to a different section of code. They are commonly used for looping and calling subroutines. RISC-V provides two jump instructions, J and JAL. The J instruction unconditionally jumps to a target address. It is often used in combination with a label to create loops or to jump to specific sections of code. Here is an example of the J instruction. J label. In this example, the program will jump to the label address without any condition. The JAL instruction is similar to J, but it also saves the address of the next instruction in the raw return address register. This allows the program to return to the original location after executing a subroutine. Here is an example of the JAL instruction. JAL label. In this example, the program will jump to the label address and save the address of the next instruction in the raw register. Branch and jump instructions in control flow. Branch and jump instructions are often used together to create complex control flow in a RISC-V assembly program. By combining these instructions with conditional statements and loops, you can create powerful and flexible programs. For example, consider the following code snippet that calculates the factorial of a number. Li x1, 5 hash load the number 5 into register x1 Li x2, 1 hash initialize the factorial variable to 1 loop. BEQ x1, x0, end hash if x1 is 0, branch to the end mul x2, x2, x1 hash multiply the factorial by x1 addy x1, x1, minus 1 hash decrement x1 by 1 j loop hash jump back to the loop label. End. In this example, the program uses a combination of branch and jump instructions to calculate the factorial of 5. It starts by loading the number 5 into register x1 and initializing the factorial variable to 1. Then, it enters a loop where it multiplies the factorial by x1, decrements x1 by 1, and jumps back to the loop label until x1 becomes 0. Finally, it reaches the end label and continues executing the next instruction. By understanding and utilizing branch and jump instructions effectively, you can create more complex and dynamic programs in RISC-V assembly. These instructions provide the necessary tools to control the flow of execution and make decisions based on specific conditions. In the next section, we will explore control flow instructions that allow for conditional branching and unconditional jumping in RISC-V assembly programs. 4. Control flow instructions. 4.1 Conditional branch instructions. Conditional branch instructions are an essential part of any assembly language programming, including RISC-V. These instructions allow the program to make decisions and alter the flow of execution based on certain conditions. In this section, we will explore the different conditional branch instructions available in RISC-V and learn how to use them effectively in our programs. Branching basics. Before diving into the specific conditional branch instructions, let's first understand the concept of branching in assembly language. Branching refers to the ability of a program to change the sequence of instructions being executed based on certain conditions. It allows the program to make decisions and execute different sets of instructions depending on the outcome of those decisions. In RISC-V, conditional branch instructions are used to implement branching. These instructions evaluate a condition and then decide whether to jump to a different instruction or continue executing the next instruction in sequence. The condition is typically based on the values of the registers or the result of a previous instruction. Conditional branch instructions in RISC-V. RISC-V provides several conditional branch instructions that allow us to implement different types of branching based on various conditions. Let's explore some of the commonly used conditional branch instructions. BEQ branch if equal, this instruction branches to the target address if the two specified registers are equal. BNE branch if not equal, this instruction branches to the target address if the two specified registers are not equal. BLT branch if less than, this instruction branches to the target address if the first specified register is less than the second specified register. BGE branch if greater than or equal, this instruction branches to the target address if the first specified register is greater than or equal to the second specified register. BLTU branch if less than, unsigned, this instruction branches to the target address if the first specified register is less than the second specified register, treating the values as unsigned. BGEU branch if greater than or equal, unsigned, this instruction branches to the target address if the first specified register is greater than or equal to the second specified register, treating the values as unsigned. These conditional branch instructions provide the flexibility to implement various decision-making scenarios in our programs. By combining these instructions with other instructions, we can create complex branching logic to handle different situations. Branching example. Let's consider a simple example to understand how conditional branch instructions work in practice. Suppose we have two variables, x and y, and we want to compare their values and perform different actions based on the result. Here's how we can achieve this using conditional branch instructions. Hash assume x is stored in register x_reg and y is stored in register y_reg. Hash compare x and y beq x_reg, y_reg, equal underscore branch bne x_reg, y_reg, not underscore equal underscore branch. Equal underscore branch. Hash code to execute if x and y are equal hash. Hash jump to the end of the comparison j end underscore comparison. Not underscore equal underscore branch. Hash code to execute if x and y are not equal hash. End underscore comparison. Hash code to continue execution after the comparison hash. In this example, we first use the BEQ instruction to check if x and y are equal. If they are equal, we branch to the equal_branch label and execute the corresponding code. If they are not equal, we branch to the not_equal_branch label and execute the corresponding code. Finally, we use the J instruction to jump to the end_comparison label and continue execution after the comparison. Summary. Conditional branch instructions are essential for implementing decision-making logic in assembly language programs. In RISC-V, we have several conditional branch instructions like BEQ, BNE, BLT, BGE, BLTU, and BGEU that allow us to branch based on different conditions. By using these instructions effectively, we can create programs that can make decisions and adapt their behavior accordingly. In the next section, we will explore another type of branch instructions called unconditional jump instructions, which allow us to jump to specific addresses without any condition. 4.2 Unconditional jump instructions. In RISC-V assembly language, unconditional jump instructions allow the program to transfer control to a different part of the code without any condition or comparison. These instructions are useful for implementing loops, function calls, and other control flow structures in a program. There are two main types of unconditional jump instructions in RISC-V, JAL jump and link and JALR jump and link register. Let's explore each of these instructions in detail. JAL jump and link. The JAL instruction is used to perform an unconditional jump to a target address specified in the instruction. It also saves the return address, the address of the instruction following the JAL instruction, into a register. This allows the program to return to the original location after executing the target code. The syntax of the JAL instruction is as follows. JAL road, IMM. Here, road is the destination register where the return address will be stored, and IMM is the immediate value representing the target address. The immediate value is calculated by taking the 20 least significant bits of the target address and appending the 12 most significant bits of the current program counter PC. For example, consider the following JAL instruction. JAL x1, 100. This instruction will jump to the target address 100 and store the return address, the address of the instruction following the JAL instruction, in register x1. JALR jump and link register. The JALR instruction is similar to the JAL instruction, but instead of using an immediate value for the target address, it uses the value stored in a register. This allows for more flexibility in determining the target address dynamically. The syntax of the JALR instruction is as follows. JALR road, 1 rupee, IMM. Here, road is the destination register where the return address will be stored, 1 rupee is the source register containing the target address, and IMM is an immediate value added to the target address. For example, consider the following JALR instruction. JALR x1, x2, 0. This instruction will jump to the address stored in register x2 and store the return address, the address of the instruction following the JALR instruction, in register x1. The immediate value 0 is added to the target address. Using unconditional jump instructions. Unconditional jump instructions are commonly used in assembly programming to implement loops and function calls. Here's an example of how these instructions can be used. Main. Hash perform some operations. JAL x1, loop. Hash continue with the rest of the program. Loop. Hash loop body. Hash check loop condition hash if condition is true, jump back to the loop JALR x0, x0, -4. In this example, the program starts executing at the main label. After performing some operations, it jumps to the loop label using the JAL instruction. The loop label represents the start of a loop. Inside the loop, there is a loop body followed by a check for the loop condition. If the condition is true, the program jumps back to the loop label using the JALR instruction with an immediate value of -4. This negative immediate value subtracts 4 from the target address, effectively jumping back to the start of the loop. Unconditional jump instructions can also be used for implementing function calls. The JAL instruction is typically used to jump to a function, and the return address is stored in a register. After executing the function, the program can use an JALR instruction to jump back to the return address stored in the register. In conclusion, unconditional jump instructions in RISC-V assembly language provide a way to transfer control to different parts of the code without any condition or comparison. These instructions are essential for implementing loops, function calls, and other control flow structures in a program. By using the JAL and JALR instructions, programmers can create efficient and flexible code that can handle complex control flow scenarios. 4.3 Procedure call and return instructions. Procedure call and return instructions are essential for organizing and managing code in RISC-V assembly language. These instructions allow the program to call and return from subroutines or functions, enabling modular and reusable code. In this section, we will explore the different procedure call and return instructions available in RISC-V. 4.3.1 Call instruction. The call instruction is used to call a subroutine or function. It transfers control to the specified address and saves the return address in the raw return address register. The call instruction is a pseudo instruction that expands into a combination of instructions to set up the stack frame and jump to the subroutine. The general syntax of the call instruction is as follows. Call label. Here, label represents the address of the subroutine or function to be called. The call instruction is typically used in conjunction with the read instruction to return from the subroutine. 4.3.2 Return instruction. The read instruction is used to return from a subroutine or function. It transfers control back to the instruction following the call instruction and restores the return address from the raw register. The read instruction is a pseudo instruction that expands into a combination of instructions to clean up the stack frame and jump back to the calling code. The general syntax of the read instruction is as follows. Ret. The read instruction does not take any operands. It simply transfers control back to the calling code. 4.3.3 Stack frame. When calling a subroutine or function, it is necessary to allocate space on the stack to store local variables and save the return address. The stack frame is a region of memory used to store these values. The stack pointer (SP) register is typically used to keep track of the top of the stack. Before calling a subroutine, the caller is responsible for allocating space on the stack for the subroutine's local variables and saving the return address. This is typically done by subtracting the required amount of space from the stack pointer and storing the return address in the appropriate location. Upon returning from a subroutine, the callee is responsible for cleaning up the stack frame by restoring the stack pointer to its original value and returning control to the calling code. 4.3.4 Example. Let's consider a simple example to illustrate the usage of procedure call and return instructions. Suppose we have a subroutine called add_numbers that takes two arguments and returns their sum. Here's how the code would look like. Add_numbers. Add A0, A1 hash add the two arguments ret hash return from the subroutine. Main. Li A0, 5 hash load argument 1 li A1, 7 hash load argument 2 call add_numbers hash call the subroutine hash the result is now stored in A0. In this example, the add_numbers subroutine adds the values of A0 and A1 and stores the result in A0. The main code loads the arguments 5 and 7 into registers A0 and A1, respectively. It then calls the add_numbers subroutine using the call instruction. After the subroutine returns, the result is stored in A0. 4.3.5 Saving and restoring registers. When calling a subroutine, it is important to preserve the values of any registers that will be modified by the subroutine. This is typically done by saving the register values on the stack before modifying them and restoring them before returning from the subroutine. The call and read instructions do not automatically save and restore registers. It is the responsibility of the programmer to explicitly save and restore any necessary registers. Conclusion. Procedure call and return instructions are fundamental to organizing and managing code in RISC-V assembly language. The call instruction is used to call a subroutine or function, while the read instruction is used to return from a subroutine. Understanding how to properly use these instructions, along with managing the stack frame and restoring registers, is crucial for writing efficient and modular code in RISC-V assembly. 4.4 Interrupt and exception handling. Interrupts and exceptions are crucial aspects of any computer system, including RISC-V. They allow the processor to respond to external events or internal errors in a controlled manner. In this section, we will explore the concepts of interrupts and exceptions, their handling mechanisms, and how to write interrupt and exception handlers in RISC-V assembly. 4.4.1 Interrupts and Exceptions Overview. Interrupts and exceptions are events that can occur during the execution of a program, causing the normal flow of execution to be temporarily suspended. While interrupts are typically triggered by external devices, such as timers or input-output devices, exceptions are usually caused by internal events, such as arithmetic errors or illegal instructions. Interrupts and exceptions serve different purposes. Interrupts are used to handle asynchronous events that require immediate attention, while exceptions are used to handle synchronous events that occur as a result of executing instructions. 4.4.2 Interrupt and exception handling in assembly. When an interrupt or exception occurs, the processor needs to handle it appropriately to ensure the system's stability and reliability. In RISC-V, interrupt and exception handling is achieved through a combination of hardware and software mechanisms. The hardware component responsible for interrupt and exception handling is the interrupt controller. It receives interrupt signals from external devices and generates interrupt requests to the processor. The interrupt controller also provides a mechanism to prioritize interrupts and manage their delivery to the processor. On the software side, RISC-V provides a set of instructions and conventions for handling interrupts and exceptions. These instructions allow the programmer to define interrupt and exception handlers, which are special routines that handle specific interrupt or exception events. 4.4.3 Interrupt and exception handlers. Interrupt and exception handlers are functions or routines that are executed when a specific interrupt or exception occurs. These handlers are responsible for performing the necessary actions to handle the event and restore the system to a stable state. In RISC-V assembly, interrupt and exception handlers are written using a specific set of instructions and conventions. The handler code is typically placed at a specific memory location called the interrupt or exception vector table. This table contains the addresses of the interrupt and exception handlers. When an interrupt or exception occurs, the processor looks up the corresponding handler address in the interrupt or exception vector table and jumps to that address to execute the handler code. Once the handler completes its execution, it returns control to the interrupted program. 4.4.4 Interrupt and Exception Vector Table. The interrupt and exception vector table is a data structure that holds the addresses of interrupt and exception handlers. It is typically located at a fixed memory location and is initialized during system startup. In RISC-V, the interrupt and exception vector table is implemented as an array of addresses. Each entry in the table corresponds to a specific interrupt or exception event. The index of the entry represents the interrupt or exception number, while the value stored at that index is the address of the corresponding handler. During system initialization, the interrupt and exception vector table is populated with the addresses of the appropriate interrupt and exception handlers. This ensures that when an interrupt or exception occurs, the processor can quickly locate and execute the corresponding handler. Conclusion. Interrupts and exceptions are essential for handling external events and internal errors in a computer system. In this section, we explored the concepts of interrupts and exceptions, their handling mechanisms, and how to write interrupt and exception handlers in RISC-V Assembly. Understanding interrupt and exception handling is crucial for developing robust and reliable RISC-V assembly programs. 5. Memory Management. 5.1 Memory Organization in RISC-V. In RISC-V assembly programming, understanding how memory is organized is crucial for writing efficient and reliable code. Memory organization refers to how the memory is divided and structured to store data and instructions. This section will provide an overview of the memory organization in RISC-V and explain the different memory regions and their purposes. Memory regions. RISC-V divides the memory into several regions, each serving a specific purpose. These regions include text segment, also known as the code segment. This region stores the program instructions. It is typically read-only and executable, meaning that the instructions can be fetched and executed by the processor. The text segment is usually located at the lower addresses of the memory. Data segment. The data segment stores initialized global and static variables. It is divided into two sub-regions, the read-only data segment raw data and the read-write data segment data. The read-only data segment contains constants and strings that cannot be modified during program execution. The read-write data segment stores global and static variables that can be modified. BSS segment. The BSS block started by symbol segment stores uninitialized global and static variables. It is typically initialized to 0 before the program starts executing. The BSS segment helps conserve memory by not allocating space for variables that are not explicitly initialized. Heap. The heap is a dynamically allocated memory region used for storing data structures such as arrays and linked lists. It grows dynamically as memory is allocated and released during program execution. The heap is managed by the programmer using memory allocation functions like malloc and free. Stack. The stack is a region of memory used for storing local variables, function call information, and return addresses. It grows and shrinks automatically as functions are called and return. The stack is organized as a last in first out LIFO data structure, meaning that the most recently pushed item is the first to be popped. Memory layout. The memory layout in RISC-V is typically organized as follows. ++ text segment ++ data segment ++ BSS segment ++ heap ++ stack ++. The text segment is located at the lowest addresses, followed by the data segment, BSS segment, heap, and stack. The stack grows downwards, while the heap grows upwards. The exact memory addresses and sizes of these regions depend on the specific hardware and operating system. Memory access. In RISC-V assembly, memory access is performed using load and store instructions. These instructions allow the processor to read from and write to memory. The load instructions transfer data from memory to registers, while the store instructions transfer data from registers to memory. The RISC-V instruction set provides different load and store instructions for accessing different data sizes: byte, half-word, word, and double word, and addressing modes immediate, register, and offset. The programmer must ensure that the correct load and store instructions are used based on the data size and memory alignment requirements. Memory alignment. Memory alignment refers to the requirement that certain data types must be stored at specific memory addresses. For example, a 32-bit word must be aligned on a 4-byte boundary, meaning that its memory address must be divisible by 4. Failure to align data properly can result in performance penalties or even program crashes on some architectures. In RISC-V, the alignment requirements vary depending on the data type. For example, byte-sized data can be stored at any memory address, while half-words must be aligned on a 2-byte boundary, words on a 4-byte boundary, and double words on an 8-byte boundary. To ensure proper alignment, the programmer must be aware of the alignment requirements of the data being accessed and use appropriate instructions and memory allocation techniques. Conclusion. Understanding the memory organization in RISC-V is essential for writing efficient and reliable assembly code. By knowing the different memory regions, their purposes, and the memory layout, programmers can optimize memory usage and ensure proper data access. Additionally, being aware of memory alignment requirements helps prevent performance issues and program crashes. 5.2 Memory Access Instructions. Memory access instructions are an essential part of any assembly language, including RISC-V. These instructions allow the processor to read from and write to memory, enabling the manipulation and storage of data during program execution. In this section, we will explore the different memory access instructions available in RISC-V and how they can be used effectively. Load instructions. Load instructions are used to retrieve data from memory and store it in a register. In RISC-V, there are several load instructions available, each designed to handle different data types and memory addressing modes. The most commonly used load instructions are LB, load byte LH, load half-word LW, load word LBU, load byte unsigned LHU, load half-word unsigned. These instructions allow you to load signed and unsigned bytes, half-words, and words from memory. The size of the loaded data depends on the instruction used. For example, LB loads a signed byte, while LBU loads an unsigned byte. Load instructions require a memory address to load data from in a register to store the loaded value. The memory address can be specified directly or calculated using a register and an offset. Here's an example of loading a word from memory into a register. LWA0, 0A1. In this example, the LW instruction loads a word from the memory address specified by the sum of the value in register A1 and the immediate offset of 0. The loaded value is then stored in register A0. Store instructions. Store instructions, on the other hand, are used to write data from a register to a memory location. Like load instructions, RISC-V provides different store instructions for different data types and addressing modes. The commonly used store instructions are SB, store byte shish, store half-word SW, store word. These instructions allow you to store bytes, half-words, and words to memory. The size of the stored data depends on the instruction used. For example, SB stores a byte, while SW stores a word. Store instructions require a register containing the data to be stored and a memory address to store the data at. Similar to load instructions, the memory address can be specified directly or calculated using a register and an offset. Here's an example of storing a word from a register to memory. SWA0, 0A1. In this example, the SW instruction stores the value in register A0 to the memory address specified by the sum of the value in register A1 and the immediate offset of 0. Memory access and alignment. When working with memory access instructions, it's important to consider memory alignment. Memory alignment refers to the requirement that certain data types must be stored at memory addresses that are multiples of their size. For example, a word 4 bytes must be stored at an address that is divisible by 4. RISC-V enforces memory alignment rules, and violating these rules can result in performance penalties or even program crashes. To ensure proper alignment, you should align your data structures and memory addresses accordingly. Endianness. Another important consideration when working with memory access instructions is endianness. Endianness refers to the order in which bytes are stored in memory. RISC-V supports both little endian and big endian byte orderings. In little endian byte ordering, the least significant byte is stored at the lowest memory address, while the most significant byte is stored at the highest memory address. In big endian byte ordering, the most significant byte is stored at the lowest memory address, and the least significant byte is stored at the highest memory address. The choice of endianness depends on the specific system and application requirements. RISC-V processors can be configured to operate in either little endian or big endian mode. Summary. Memory access instructions are crucial for manipulating and storing data during program execution. In RISC-V, load instructions retrieve data from memory and store it in registers, while store instructions write data from registers to memory. These instructions support different data types and addressing modes, allowing for flexible memory access. When working with memory access instructions, it's important to consider memory alignment and endianness. Proper alignment ensures optimal performance and prevents crashes, while endianness determines the byte ordering in memory. Understanding and effectively using memory access instructions is essential for writing efficient and functional RISC-V assembly programs. With the knowledge gained from this section, you can now confidently work with memory in your RISC-V programs. 5.3 Stack and stack operations. In computer programming, a stack is a data structure that stores information in a last-in, first-out (LIFO) manner. It is commonly used to manage function calls and local variables in a program. The RISC-V architecture provides instructions to manipulate the stack, allowing programmers to efficiently allocate and deallocate memory for function calls and local variables. The stack pointer. In RISC-V, the stack pointer (SP) register is used to keep track of the top of the stack. It points to the memory location where the next value will be pushed onto the stack. The stack grows downwards in memory, so as values are pushed onto the stack pointer decreases. Pushing and popping values. To push a value onto the stack, the SW store word instruction is used. This instruction stores a value from a register into memory at the address specified by the stack pointer. After the value is stored, the stack pointer is decremented to point to the next available memory location. Here is an example of pushing a value onto the stack. ADD -4 hash decrement stack pointer by 4 bytes SWA0, 0 SP hash store value from register A0 onto the stack. To pop a value from the stack, the LW load word instruction is used. This instruction loads a value from memory at the address specified by the stack pointer into a register. After the value is loaded, the stack pointer is incremented to point to the next value on the stack. Here is an example of popping a value from the stack. LWA0, 0 SP hash load value from stack into register A0 ADD SP 4 hash increment stack pointer by 4 bytes stack frame. A stack frame is a block of memory on the stack that is used to store information related to a function call. It typically includes the return address, function arguments, local variables, and saved registers. The stack frame is created when a function is called and destroyed when the function returns. The stack frame is organized as follows. Return address, the address to which the program should return after the function call is completed. Function arguments, values passed to the function. Local variables, variables declared within the function. Saved registers, registers that need to be preserved across function calls. The stack frame is managed using the stack pointer. When a function is called, the stack pointer is decremented to allocate space for the stack frame. The function arguments and local variables are then stored in the allocated space. When the function returns, the stack pointer is incremented to deallocate the stack frame. Example, function call with stack frame. Let's consider an example of a function call with a stack frame. Assume we have a function add_numbers that takes 2 arguments and returns their sum. Here is the assembly code for the function. Add_numbers. Add A0, a 1 hash add the 2 arguments junior raw hash jump back to the return address. To call the add_numbers function, we need to set up the stack frame. Here is the assembly code for the function call. Main. ADD SP -8 hash decrement stack pointer by 8 bytes to allocate space for the stack frame SW-raw, 0 SP hash save the return address on the stack SWA0, 4 SP hash save the first argument on the stack SWA1, 8 SP hash save the second argument on the stack. JAL-raw, add_numbers hash call the add_numbers function. LWA0, 0 SP hash load the return value from the stack ADD SP 8 hash increment stack pointer by 8 bytes to deallocate the stack frame. In this example, we first decrement the stack pointer by 8 bytes to allocate space for the stack frame. We then save the return address, first argument, and second argument on the stack. After calling the add_numbers function, we load the return value from the stack and increment the stack pointer to deallocate the stack frame. Conclusion. Understanding stack operations is essential for writing efficient and reliable assembly code. By properly managing the stack, you can allocate and deallocate memory for function calls and local variables. The stack frame provides a structured way to organize information related to function calls. By using the stack pointer and instructions like SW and LW, you can push and pop values onto and from the stack. 5.4 Heap and Dynamic Memory Allocation. In RISC-V Assembly, memory management plays a crucial role in efficiently utilizing the available memory resources. One important aspect of memory management is dynamic memory allocation, which allows programs to request memory at runtime and release it when it is no longer needed. This section will explore the concept of the heap and how dynamic memory allocation can be achieved in RISC-V Assembly. The heap. The heap is a region of memory that is used for dynamic memory allocation. Unlike the stack, which is managed automatically by the processor, the heap requires explicit management by the programmer. The heap is typically used for storing data structures that have a variable size or need to persist beyond the lifetime of a function. In RISC-V Assembly, the heap is not directly accessible. Instead, it is managed through system calls provided by the operating system. These system calls allow programs to request memory from the operating system and release it when it is no longer needed. The operating system keeps track of the allocated memory blocks and ensures that they are properly managed. Dynamic memory allocation. Dynamic memory allocation refers to the process of requesting memory from the operating system at runtime. This is typically done using the SBRK system call, which allows programs to increase or decrease the size of the heap. The SBRK system call takes a single argument, which specifies the number of bytes to be added or subtracted from the heap. To allocate memory on the heap, the program needs to calculate the size of the memory block required and pass it as an argument to the SBRK system call. The return value of the SBRK system call is a pointer to the start of the allocated memory block. This pointer can then be used to access and manipulate the allocated memory. Here is an example of how dynamic memory allocation can be achieved in RISC-V Assembly. Hash allocate 100 bytes on the heap LA0, 100. LA7, 9 hash SBRK system call number eCall. MVT0, a 0 hash T0 contains the pointer to the allocated memory. Hash use the allocated memory hash. Hash release the allocated memory MVA0, T0 hash A0 contains the pointer to the allocated memory LA7, 10 hash SBRK system call number eCall. In this example, the program first sets the size of the memory block to be allocated in register A0. It then sets the system call number for SBRK in register A7 and makes a system call using the eCall instruction. The return value of the system call, which is the pointer to the allocated memory, is stored in register A0 and then moved to register T0 for later use. After using the allocated memory, the program can release it by passing the pointer to the SBRK system call again. This time, the system call number for releasing memory is used, and the memory block is returned to the operating system. Memory management best practices. When using dynamic memory allocation in RISC-V assembly, it is important to follow some best practices to ensure efficient memory usage and avoid memory leaks. Here are a few tips. Always release allocated memory when it is no longer needed. Failing to release memory can lead to memory leaks and eventually exhaust the available memory. Avoid excessive use of dynamic memory allocation. Allocating and releasing memory frequently can be time-consuming and may impact the performance of the program. Whenever possible, try to use static memory allocation or reuse existing memory blocks. Be mindful of memory fragmentation. As memory blocks are allocated and released, the heap can become fragmented, leading to inefficient memory usage. Consider using memory allocation algorithms that minimize fragmentation, such as buddy allocation or memory pooling. Use appropriate data structures and algorithms. Choosing the right data structures and algorithms can significantly impact memory usage. Consider the space and time complexity of different data structures and choose the most efficient one for your specific use case. By following these best practices, you can effectively manage dynamic memory allocation in your RISC-V assembly programs and optimize memory usage for better performance. In conclusion, dynamic memory allocation is an essential aspect of memory management in RISC-V assembly. By understanding the concept of the heap and using system calls like SBRK, programs can request and release memory at runtime. Following best practices for memory management can help optimize memory usage and improve the overall performance of your RISC-V assembly programs. 6. Input and output operations. 6.1 Input and output devices in RISC-V. Input and output I/O operations are essential for any computer system, including those based on the RISC-V architecture. In this section, we will explore the various input and output devices that can be used with RISC-V systems. Input devices. Input devices allow users to provide data or commands to the computer system. Some common input devices that can be used with RISC-V systems include keyboard. A keyboard is a primary input device that allows users to enter text and commands. RISC-V systems can interface with keyboards using standard protocols such as USB or PS2. Mouse. A mouse is a pointing device that allows users to control the cursor on the screen. RISC-V systems can connect to mice using USB or other compatible interfaces. Touchscreen. Touchscreens are input devices that allow users to interact with the system by touching the display directly. RISC-V systems can support touchscreens through specialized controllers and drivers. Gamepad. Gamepads are input devices commonly used for gaming. RISC-V systems can interface with gamepads using USB or other compatible interfaces. Sensors. Various sensors, such as temperature sensors, motion sensors, and proximity sensors, can be used as input devices with RISC-V systems. These sensors provide data about the physical environment to the system. Output devices. Output devices display or present information generated by the computer system. Some common output devices that can be used with RISC-V systems include monitor. A monitor or display is the primary output device for most computer systems. RISC-V systems can connect to monitors using standard interfaces such as HDMI or VGA. Printer. Printers are used to produce hard copies of documents or images. RISC-V systems can interface with printers using USB or other compatible interfaces. Speaker. Speakers are used to produce audio output. RISC-V systems can connect to speakers using audio jacks or other compatible interfaces. LEDs. Light-emitting diodes (LEDs) can be used as simple output devices to indicate the status of the system or provide visual feedback. RISC-V systems can control LEDs through GPIO, general-purpose input-output pins. Actuators. Actuators, such as motors or solenoids, can be used as output devices to control physical mechanisms. RISC-V systems can interface with actuators through specialized controllers and drivers. Communication interfaces. In addition to the specific input and output devices mentioned above, RISC-V systems can also communicate with external devices through various interfaces. Some common communication interfaces used in RISC-V systems include Universal Serial Bus (USB). USB is a widely used interface that allows for the connection of a variety of devices, including keyboards, mice, printers, and storage devices. Ethernet. Ethernet is a standard communication protocol used for connecting devices in a local area network (LAN). RISC-V systems can use Ethernet interfaces to communicate with other devices on the network. Serial communication. Serial communication interfaces, such as UART (Universal Asynchronous Receiver Transmitter), allow for the transmission of data one bit at a time. RISC-V systems can use serial communication interfaces to communicate with devices such as GPS modules or RFID readers. Inter-integrated circuit I2C. I2C is a communication protocol commonly used for connecting low-speed peripherals to microcontrollers and embedded systems. RISC-V systems can use I2C interfaces to communicate with sensors, displays, and other devices. Serial Peripheral Interface SPI. SPI is a synchronous serial communication interface commonly used for connecting microcontrollers to peripheral devices. RISC-V systems can use SPI interfaces to communicate with devices such as flash memory chips or digital-to-analog converters. These communication interfaces provide RISC-V systems with the ability to interact with a wide range of devices and expand their functionality. In the next section, we will explore how to read and write data using RISC-V assembly language. 6.2 Reading and Writing Data. In this section, we will explore how to read and write data in RISC-V assembly language. Reading and writing data is an essential part of any programming language, as it allows us to interact with the user and manipulate data stored in memory. Reading data. To read data from the user in RISC-V assembly, we can use the load immediate instruction to load a system call number into register A7 and then use the eCall instruction to invoke the system call. The system call number for reading data is 63. Here is an example of how to read an integer from the user. A7, 63 load system call number for reading data eCall invoke the system call. The read data will be stored in register A0. After executing the above code, the user will be prompted to enter an integer value. The entered value will be stored in register A0, which can then be used for further processing. Similarly, we can read a character from the user by using the system call number 64. Here is an example. A7, 64 load system call number for reading character eCall invoke the system call. The read character will be stored in register A0 writing data. To write data in RISC-V assembly, we can use the instruction to load the system call number for writing data into register A7, and then use the eCall instruction to invoke the system call. The system call number for writing data is 64. Here is an example of how to write an integer to the console. A7, 64 load system call number for writing data A0, 42 load the integer value to be written eCall invoke the system call. After executing the above code, the value 42 will be written to the console. Similarly, we can write a character to the console by using the system call number 65. Here is an example. A7, 65 load system call number for writing character A0, load the character to be written eCall invoke the system call. After executing the above code, the character, A, will be written to the console. String input and output. In addition to reading and writing individual characters and integers, we can also read and write strings in RISC-V assembly. To read a string from the user, we can use the system call number 80. The string will be stored in a buffer pointed to by register A0, and the maximum number of characters to read can be specified in register A1. Here is an example of how to read a string from the user. A7, 80 load system call number for reading string A0, buffer load the address of the buffer to store the string A1, 100 load the maximum number of characters to read eCall invoke the system call. The read string will be stored in the buffer. After executing the above code, the user will be prompted to enter a string. The entered string will be stored in the buffer specified by register A0. To write a string to the console, we can use the system call number 64. The string should be null terminated, meaning it should end with a null character, ASCII value 0. Here is an example of how to write a string to the console. A7, 64 load system call number for writing data A0, message load the address of the string to be written eCall invoke the system call. Data. Message, ASCIIZ, hello, world. The string to be written after executing the above code, the string, hello, world, will be written to the console. Conclusion. Reading and writing data is an essential part of any programming language, and RISC-V assembly provides the necessary instructions to perform these operations. In this section, we learned how to read and write individual characters, integers, and strings in RISC-V assembly. These operations allow us to interact with the user and manipulate data stored in memory, enabling us to build more complex and interactive programs. 6.3 Interrupt-driven input and output. In traditional input and output I/O operations, the processor waits for the completion of each I/O operation before proceeding to the next instruction. This can be inefficient, especially when dealing with slow I/O devices or when multiple devices need to be serviced simultaneously. Interrupt-driven I/O provides a solution to this problem by allowing the processor to continue executing other instructions while waiting for I/O operations to complete. Interrupt-driven I/O works by using interrupts, which are signals generated by I/O devices to request attention from the processor. When an I/O device needs to transfer data or complete an operation, it raises an interrupt signal to the processor. The processor then suspends its current execution and transfers control to an interrupt handler routine, which is a special section of code designed to handle the specific interrupt. To implement interrupt-driven I/O in RISC-V assembly, we need to understand the interrupt handling mechanism provided by the RISC-V architecture. RISC-V supports two types of interrupts: external interrupts and software interrupts. External interrupts are generated by external devices, such as timers, keyboards, or network interfaces. These interrupts are handled by the external interrupt controller, which is responsible for detecting and forwarding the interrupt signals to the processor. When an external interrupt occurs, the processor saves its current state and transfers control to the external interrupt handler routine. Software interrupts, on the other hand, are generated by software instructions. These interrupts are typically used for system calls or other software-related events. When a software interrupt instruction is executed, the processor saves its current state and transfers control to the software interrupt handler routine. To enable interrupt-driven I/O, we need to configure the interrupt controller and set up the interrupt handler routines. The specific steps may vary depending on the RISC-V implementation and the development environment being used. However, the general process involves the following. Configuring the interrupt controller. The interrupt controller needs to be configured to enable interrupts from the desired devices. This typically involves setting specific registers or memory map locations to enable interrupt sources and define their priorities. Setting up interrupt handlers. Interrupt handlers are special sections of code that handle specific interrupts. Each interrupt has its own handler routine, which is responsible for performing the necessary actions when the interrupt occurs. The interrupt handlers need to be written in assembly language and placed at specific memory locations or linked to specific interrupt vectors. Enabling interrupts. Once the interrupt controller and interrupt handlers are set up, interrupts need to be enabled in the processor. This is typically done by setting specific bits in the processor's status register or control registers. Handling interrupts. When an interrupt occurs, the processor automatically saves its current state and transfers control to the corresponding interrupt handler routine. The interrupt handler performs the necessary actions, such as reading or writing data from to I/O devices, and then returns control to the interrupted program. Interrupt-driven I/O provides several advantages over traditional I/O operations. First, it allows the processor to perform other tasks while waiting for I/O operations to complete, improving overall system efficiency. Second, it enables concurrent processing of multiple I/O operations, allowing for better utilization of I/O devices. Finally, it simplifies the programming model by abstracting the low-level details of I/O operations, making it easier to write and maintain code. However, interrupt-driven I/O also introduces some challenges. Interrupt handlers need to be carefully designed to handle interrupts efficiently and avoid potential race conditions or deadlocks. Additionally, interrupt-driven I/O requires careful synchronization and coordination between the interrupt handlers and the main program to ensure data integrity and prevent conflicts. In conclusion, interrupt-driven I/O is a powerful technique for improving the efficiency and performance of I/O operations in RISC-V assembly. By leveraging interrupts and interrupt handlers, we can enable the processor to perform other tasks while waiting for I/O operations to complete, leading to more efficient and responsive systems. However, it is important to carefully design and manage interrupt handlers to ensure proper synchronization and avoid potential issues. 6.4 File Operations. In this section, we will explore how to perform file operations in RISC-V assembly language. File operations are essential for reading and writing data to external storage devices such as hard drives, solid-state drives, or even network storage. Understanding file operations is crucial for building real-world applications that require data persistence. File I/O concepts. Before diving into the specifics of file operations in RISC-V assembly, let's briefly discuss some fundamental concepts related to file input and output. File streams. In most programming languages, file operations are performed using file streams. A file stream is a connection between a program and a file, allowing the program to read from or write to the file. In RISC-V assembly, file streams are typically represented by file descriptors, which are integer values that uniquely identify an open file. Opening a file. To perform file operations, we first need to open the file. The open system call is used to open a file and obtain a file descriptor. The open system call takes the file name and a set of flags as arguments and returns a file descriptor if successful. The flags specify the mode in which the file should be opened, such as read-only, write-only, or read-write. Reading from a file. Once a file is opened, we can read data from it using the read system call. The read system call takes the file descriptor, a buffer to store the read data, and the number of bytes to read as arguments. It returns the number of bytes actually read. If the return value is less than the requested number of bytes, it indicates the end of the file has been reached. Writing to a file. To write data to a file, we use the write system call. The write system call takes the file descriptor, a buffer containing the data to write, and the number of bytes to write as arguments. It returns the number of bytes actually written. If the return value is less than the requested number of bytes, it indicates an error occurred during the write operation. Closing a file. After we have finished performing file operations, it is important to close the file to release system resources. The close system call is used to close a file. It takes the file descriptor as an argument and returns 0 if successful. File operations in RISC-V assembly. To perform file operations in RISC-V assembly, we need to use the appropriate system calls. The system calls for file operations are typically accessed through the ecall instruction. Let's take a look at an example that demonstrates how to open, read from, write to, and close a file in RISC-V Assembly. Data. File name, ASCIIZ, example.txt, buffer, space 256. Text, global main. Hash open the file lia0, 0 hash file name address lia1, file name. lia2, 2 hash flags, read and write lia7, 1024 hash system call number for open eCall. MVS0, a 0 hash save the file descriptor in S0. Hash read from the file lia0, 1 hash file descriptor lia1, buffer. lia2, 256 hash number of bytes to read lia7, 63 hash system call number for read eCall. Hash write to the file lia0, 1 hash file descriptor lia1, buffer. lia2, 256 hash number of bytes to write lia7, 64 hash system call number for write eCall. Hash close the file mva0, s0 hash file descriptor lia7, 57 hash system call number for close eCall. Hash exit the program. lia7, 10 hash system call number for exit eCall. In this example, we first open the file, example.txt, with read and write permissions. We then read data from the file into a buffer and write the same data back to the file. Finally, we close the file and exit the program. It is important to note that the specific system call numbers may vary depending on the RISC-V implementation and operating system. Therefore, it is essential to consult the documentation for the specific RISC-V platform you are using to determine the correct system call numbers. Conclusion. File operations are crucial for working with external storage devices and building real-world applications. In this section, we explored the concepts of file streams, opening, reading from, writing to, and closing files in RISC-V Assembly. By understanding these concepts and using the appropriate system calls, you can effectively perform file operations in your RISC-V Assembly programs. 7. Assembly Language Programming Techniques. 7.1 Data Representation in Assembly. In assembly language programming, data representation is a fundamental concept that allows us to store and manipulate different types of data in a computer's memory. Understanding how data is represented in assembly is crucial for writing efficient and correct programs. In this section, we will explore the various data representation techniques used in RISC-V Assembly. Binary representation. At the lowest level, all data in a computer is represented using binary digits, or bits. A bit can have two possible values, 0 or 1. These binary digits are grouped together to represent larger units of data. For example, a group of 8 bits is called a byte, and it can represent values from 0 to 255. In RISC-V Assembly, binary representation is used to represent integers, characters, and other types of data. For example, the binary representation of the decimal number 10 is 00001010. In assembly, we can use the byte directive to store this binary representation in memory. Data. MyByte, byte 00001010 hexadecimal representation. While binary representation is the most fundamental way to represent data, it can be cumbersome to work with and read. Hexadecimal representation provides a more compact and human-readable alternative. Hexadecimal, or hex, uses base 16 instead of base 2 like binary. It uses the digits 0 to 9 and the letters AF to represent values from 0 to 15. In RISC-V Assembly, we can use the word directive to store hexadecimal values in memory. For example, the hexadecimal representation of the decimal number 10 is hexadecimal A. Data. MyWord, word hexadecimal A character representation. Characters are an essential part of many programs, and they are represented using a character encoding scheme. The most common character encoding scheme is ASCII, American Standard Code for Information Interchange, which assigns a unique numerical value to each character. In RISC-V Assembly, characters can be represented using their ASCII values. For example, the ASCII value for the letter A is 65. We can use the byte directive to store characters in memory. Data. MyChar, byte 65 string representation. Strings are sequences of characters, and they are commonly used in programming. In RISC-V Assembly, strings are represented as arrays of characters, terminated by a null character, ASCII value 0. To represent a string in assembly, we can use the ASCIIZ directive. The Z in ASCIIZ stands for 0 terminated, indicating that the string is terminated by a null character. Data. MyString, ASCIIZ, hello, world. Floating point representation. In addition to integers and characters, RISC-V Assembly also supports floating point numbers. Floating point numbers are represented using the IEEE 754 standard, which defines formats for single precision 32-bit and double precision 64-bit floating point numbers. In RISC-V Assembly, we can use the float directive to store single precision floating point numbers and the double directive to store double precision floating point numbers. Data. MyFloat, float 3.14 MyDouble, double 3.14159 data alignment. Data alignment refers to the memory address at which a data item is stored. In RISC-V assembly, data alignment is important for performance reasons. Most RISC-V processors require data to be aligned to specific boundaries, such as 4-byte or 8-byte boundaries. To ensure proper data alignment, we can use the align directive. The argument to the align directive specifies the desired alignment in bytes. Data. My aligned data, align 4. By understanding and utilizing these data representation techniques in RISC-V assembly, you will be able to effectively store and manipulate different types of data in your programs. This knowledge is essential for writing efficient and correct assembly code. 7.2 Working with arrays and strings. In assembly language programming, arrays and strings are fundamental data structures that allow us to store and manipulate multiple values in a sequential manner. In this section, we will explore how to work with arrays and strings in RISC-V assembly. Declaring and accessing arrays. To declare an array in RISC-V assembly, we need to allocate a contiguous block of memory to store the elements of the array. This can be done using the data section of the assembly program. Let's consider an example where we want to declare an array of integers. Data. Array, word 1, 2, 3, 4, 5. In this example, we have declared an array named array and initialized it with 5 integers. Each integer is represented by the word directive, which reserves 4 bytes of memory for each element. To access individual elements of the array, we can use the base address of the array and an offset. The base address is the memory address where the array starts, and the offset is the number of bytes to add to the base address to reach a specific element. In RISC-V assembly, we can use the load address instruction to load the base address of the array into a register. Then, we can use the LW load word instruction to load the value of a specific element into another register. A0 array hash load the base address of the array into register A0 LWA1. For A0 hash load the value of the second element into register A1. In this example, we load the base address of the array into register A0 using the LA instruction. Then, we load the value of the second element, offset by 4 bytes from the base address, into register A1 using the LW instruction. Modifying array elements. To modify the value of an element in an array, we can use the SW store word instruction. Similar to accessing array elements, we need to load the base address of the array into a register and calculate the offset to the desired element. Then, we can store a new value into that memory location using the SW instruction. A0 array hash load the base address of the array into register A0 A1. 10 hash load the new value into register A1 SW-A1, 8 A0 hash store the new value into the third element of the array. In this example, we load the base address of the array into register A0 using the LA instruction. Then, we load the new value 10 into register A1 using the LI load immediate instruction. Finally, we store the new value into the third element, offset by 8 bytes from the base address of the array using the SW instruction. Working with strings. Strings in assembly language are represented as arrays of characters. Each character is stored as an ASCII value in memory. To declare a string in RISC-V assembly, we can use the ASCIIZ directive, which reserves memory for the string and adds a null terminator at the end. Data. Message, ASCIIZ, hello, world. In this example, we have declared a string named message and initialized it with the text, hello, world. The null terminator is automatically added at the end of the string. To access individual characters of a string, we can use the same technique as accessing array elements. We load the base address of the string into a register and calculate the offset to the desired character. Then, we can load or store the ASCII value of the character using the LB load byte or SB store byte instructions, respectively. A0 message hash load the base address of the string into register A0 LBA1. 7 A0 hash load the ASCII value of the 8th character into register A1. In this example, we load the base address of the string into register A0 using the LA instruction. Then, we load the ASCII value of the 8th character, offset by 7 bytes from the base address, into register A1 using the LB instruction. Similarly, we can modify individual characters of a string by storing a new ASCII value into the corresponding memory location using the SB instruction. A0 message hash load the base address of the string into register A0 LA1. Hash load the new ASCII value into register A1 SBA1. 12 A0 hash store the new ASCII value into the 13th character of the string. In this example, we load the base address of the string into register A0 using the LA instruction. Then, we load the new ASCII value into register A1 using the LI instruction. Finally, we store the new ASCII value into the 13th character, offset by 12 bytes from the base address of the string using the SB instruction. Working with arrays and strings in RISC-V assembly allows us to manipulate and process data efficiently. By understanding how to declare, access, and modify elements, we can build more complex algorithms and programs that involve arrays and strings. 7.3 Bit manipulation techniques. Bit manipulation is a fundamental skill in assembly language programming. It involves manipulating individual bits within a register to perform various operations such as setting, clearing, toggling, or extracting specific bits. In this section, we will explore some common bit manipulation techniques in RISC-V assembly. Bitwise operators. RISC-V provides several bitwise operators that allow you to manipulate individual bits within a register. These operators include an AND OR or XOR, XOR, and NOT. The AND operator AND performs a bitwise AND operation between two operands, setting the result bit to 1 only if both corresponding bits are 1. This operator is often used to clear specific bits by ANDing them with 0. The OR operator OR performs a bitwise OR operation between two operands, setting the result bit to 1 if either of the corresponding bits is 1. This operator is commonly used to set specific bits by ORing them with 1. The XOR operator XOR performs a bitwise XOR operation between two operands, setting the result bit to 1 if the corresponding bits are different. This operator is useful for toggling specific bits by XORing them with 1. The NOT operator NOT performs a bitwise NOT operation on a single operand, flipping all the bits. This operator is often used to complement specific bits by noting them. Setting and clearing bits. To set a specific bit in a register, you can use the OR operator or to OR the register with a mask that has only the desired bit set to 1. For example, to set the third bit of register X, you can use the following code. Lead T0, 0x4 load the mask with the third bit set to 1 or X, T0 OR the register with the mask to set the third bit. To clear a specific bit in a register, you can use the AND operator AND2 in the register with a mask that has only the desired bit set to 0. For example, to clear the fifth bit of register X, you can use the following code. Lead T0, hexadecimal FFFFFFDF load the mask with the fifth bit set to 0 and X, T0 in the register with the mask to clear the fifth bit toggling bits. To toggle a specific bit in a register, you can use the XOR operator XOR to XOR the register with a mask that has only the desired bit set to 1. For example, to toggle the second bit of register X, you can use the following code. Lead T0, 0x2 load the mask with the second bit set to 1 XOR X, T0 XOR the register with the mask to toggle the second bit extracting bits. To extract a specific bit from a register, you can use the AND operator AND2 in the register with a mask that has only the desired bit set to 1. For example, to extract the fourth bit of register X, you can use the following code. Lead T0, 0x8 load the mask with the fourth bit set to 1 and T1, T0 in the register with the mask to extract the fourth bit. The result will be stored in register T1, and it will contain either 0 or 1, depending on the value of the fourth bit in register X. Shifting bits. Bit shifting is another common bit manipulation technique that involves moving the bits within a register to the left or right. RISC-V provides two shift operators, logical shift left (SLL) and logical shift right (SRL). The logical shift left (SLL) operator shifts the bits in a register to the left by a specified number of positions. The shifted bits are filled with zeros. For example, to shift the bits in register X to the left by 3 positions, you can use the following code. SLLX, X3 shift the bits in register X to the left by 3 positions. The logical shift right (SRL) operator shifts the bits in a register to the right by a specified number of positions. The shifted bits are filled with zeros. For example, to shift the bits in register X to the right by 2 positions, you can use the following code. SRLX, X2 shift the bits in register X to the right by 2 positions. Conclusion. Bit manipulation techniques are essential for performing various operations in RISC-V assembly language programming. By using bitwise operators and shift operators, you can set, clear, toggle, and extract specific bits within a register. These techniques are particularly useful when working with low-level hardware interfaces, implementing algorithms, or optimizing code for performance. Understanding and mastering these techniques will greatly enhance your ability to write efficient and effective assembly programs. 7.4 Optimization Techniques. Optimization is a crucial aspect of assembly language programming. It involves making modifications to the code to improve its efficiency, speed, and overall performance. In this section, we will explore some optimization techniques specific to RISC-V assembly language programming. 7.4.1 Register Allocation. One of the key optimization techniques in RISC-V assembly is efficient register allocation. Registers are the fastest storage locations in a processor, and utilizing them effectively can significantly improve the performance of your code. To optimize register allocation, you should aim to minimize the number of memory accesses and maximize the use of registers for storing frequently accessed data. This can be achieved by carefully analyzing your code and identifying variables that are used frequently. By assigning these variables to registers, you can reduce the number of memory accesses required, resulting in faster execution. Additionally, you should also consider the use of temporary registers for intermediate calculations. By using temporary registers instead of memory locations, you can avoid unnecessary memory accesses and improve the overall efficiency of your code. 7.4.2 Loop Unrolling. Loop unrolling is a technique that involves duplicating loop iterations to reduce the overhead of loop control instructions. By unrolling loops, you can reduce the number of branch instructions and improve the overall performance of your code. To apply loop unrolling, you need to carefully analyze the loop and identify the number of iterations that can be safely unrolled. By duplicating the loop body multiple times, you can reduce the number of branch instructions and improve the efficiency of your code. However, it's important to note that loop unrolling may not always result in performance improvements. Unrolling loops can increase the code size, which may lead to cache misses and slower execution. Therefore, it's essential to consider the trade-off between code size and performance when applying loop unrolling. 7.4.3 Instruction Scheduling. Instruction scheduling is another optimization technique that aims to reorder instructions to minimize pipeline stalls and improve the overall performance of your code. In RISC-V Assembly, instructions are executed in a pipelined manner, where each stage of the pipeline performs a specific operation. However, certain instructions may introduce stalls or dependencies that can delay the execution of subsequent instructions. By carefully reordering instructions, you can minimize these stalls and improve the efficiency of your code. This can be achieved by identifying independent instructions and rearranging them to maximize the utilization of the pipeline. It's important to note that instruction scheduling can be a complex task, as it requires a deep understanding of the underlying hardware architecture and the specific pipeline stages of the processor. Therefore, it's recommended to use advanced tools and compilers that can automatically perform instruction scheduling optimizations. 7.4.4 Constant Folding and Propagation. Constant folding and propagation are optimization techniques that involve evaluating constant expressions at compile time and replacing them with their computed values. In RISC-V Assembly, constant folding and propagation can eliminate unnecessary computations and reduce the number of instructions required to perform a specific operation. By replacing constant expressions with their computed values, you can improve the efficiency of your code and reduce the overall execution time. To apply constant folding and propagation, you need to identify constant expressions in your code and evaluate them at compile time. This can be done by analyzing the code and identifying expressions that involve only constants or variables with known values. By performing constant folding and propagation, you can reduce the number of instructions required to perform a specific operation and improve the overall performance of your code. 7.4.5 Code Size Optimization. Code size optimization is an important aspect of assembly language programming, especially in resource-constrained environments. By reducing the size of your code, you can improve the utilization of memory and cache, resulting in faster execution and improved performance. To optimize code size, you should aim to eliminate unnecessary instructions, reduce the usage of large immediate values, and minimize the number of branches and jumps. Additionally, you can also consider using smaller instruction formats, such as compressed instructions, to further reduce the code size. It's important to note that code size optimization may involve trade-offs with performance. Reducing the code size can sometimes result in slower execution due to increased cache misses or additional instructions required for decompression. Therefore, it's essential to carefully analyze the specific requirements of your application and strike a balance between code size and performance. In conclusion, optimization techniques play a crucial role in improving the efficiency and performance of RISC-V assembly code. By applying techniques such as register allocation, loop unrolling, instruction scheduling, constant folding and propagation, and code size optimization, you can significantly enhance the execution speed and overall performance of your code. However, it's important to carefully analyze the specific requirements of your application and consider the trade-offs between different optimization techniques to achieve the best results. 8. Debugging and testing assembly programs. 8.1 Debugging tools and techniques. Debugging is an essential part of the software development process. It involves identifying and fixing errors or bugs in a program to ensure its proper functionality. In this section, we will explore various debugging tools and techniques that can be used to debug RISC-V assembly programs. 8.1.1 Debugging Tools 1. RISC-V Debug Module. The RISC-V Debug Module is a hardware component that provides debugging capabilities for RISC-V processors. It allows developers to halt the execution of a program, inspect and modify the processor's state, and control the program's execution. The debug module can be accessed using the Debug Transport Module (DTM) interface, which provides a standardized way to communicate with the debug module. 2. RISC-V New Debugger (GDB). GDB is a powerful command line debugger that supports RISC-V architecture. It allows developers to set breakpoints, step through the code, examine and modify variables, and analyze the program's execution. GDB can be used with RISC-V processors through the Open On-Chip Debugger, OpenOCD, or JTAG interfaces. 3. RISC-V Emulators. Emulators provide a virtual environment to run and debug RISC-V assembly programs. They simulate the behavior of a RISC-V processor and allow developers to execute and debug their programs without the need for physical hardware. Some popular RISC-V emulators include Spike, QEMU, and RARS, RISC-V Assembler and Runtime Simulator. 4. Integrated Development Environments (IDEs). IDEs such as Visual Studio Code, Eclipse, and Atom provide a comprehensive development environment for writing, debugging, and testing RISC-V assembly programs. They offer features like syntax highlighting, code completion, and integrated debugging tools, making the development process more efficient and productive. 8.1.2 Debugging Techniques 1. Breakpoints. Breakpoints are markers placed in the code that instruct the debugger to pause the program's execution at a specific line or address. By setting breakpoints at critical points in the code, developers can examine the program's state and variables at that particular moment. This technique is useful for identifying the cause of a bug or error. 2. Step-by-step execution. Stepping through the code allows developers to execute the program line by line, examining the changes in the processor's state and variables at each step. This technique helps in understanding the flow of the program and identifying any unexpected behavior or errors. 3. Variable inspection. Inspecting variables during debugging provides valuable insights into their values and how they change during program execution. Developers can examine the values of variables, registers, and memory locations to identify any incorrect or unexpected values that may be causing the bug. 4. Stack traces. A stack trace is a list of function calls that shows the sequence of function invocations leading up to the current point in the program. It helps in understanding the program's execution flow and identifying the source of an error or exception. Stack traces are particularly useful when dealing with crashes or unexpected program terminations. 5. Debugging output. Adding debug output statements to the code can help in understanding the program's behavior and identifying the cause of a bug. Developers can print variable values, function calls, or other relevant information to the console or a log file. This technique is especially useful when debugging complex or hard to reproduce issues. 6. Unit testing. Unit testing involves writing small, focused tests for individual functions or modules of the program. By testing each component in isolation, developers can quickly identify and fix bugs before they propagate to other parts of the program. Unit testing frameworks like Unity or CPP-U-Test can be used to automate the testing process. Conclusion. Debugging is an essential skill for any software developer, and it becomes even more critical when working with low-level languages like RISC-V Assembly. Understanding the available debugging tools and techniques can greatly improve the efficiency and effectiveness of the debugging process. By using tools like the RISC-V debug module, GDB, emulators, and IDEs, and employing techniques like breakpoints, step-by-step execution, variable inspection, stack traces, debugging output, and unit testing, developers can effectively debug their RISC-V assembly programs and ensure their proper functionality. 8.2 Testing Strategies for Assembly Programs. Testing is an essential part of software development, including assembly programming. It helps ensure that your code functions correctly and meets the desired requirements. In this section, we will explore various testing strategies that you can employ when working with RISC-V assembly programs. 8.2.1 Unit testing. Unit testing involves testing individual units or components of your code in isolation. In the context of assembly programming, a unit can be a single function or a small section of code. The goal is to verify that each unit performs as expected. To perform unit testing in RISC-V assembly, you can create test cases that provide specific inputs to your code and verify the outputs against expected results. For example, if you have a function that performs arithmetic operations, you can create test cases with different input values and compare the output with the expected result. Unit testing can be done manually by writing test cases and comparing the results, or you can use automated testing frameworks specifically designed for assembly programming. These frameworks provide tools and libraries to simplify the process of writing and executing test cases. 8.2.2 Integration testing. Integration testing focuses on testing the interaction between different components or modules of your code. In the context of assembly programming, this involves testing how different functions or sections of code work together. To perform integration testing, you can create test cases that cover different scenarios where multiple components interact. For example, if you have a program that reads input from a user and performs calculations, you can create test cases that simulate user input and verify the output. Integration testing can help identify issues that may arise due to the interaction between different components. It ensures that your code functions correctly as a whole and not just as individual units. 8.2.3 Regression testing. Regression testing involves retesting previously tested code to ensure that changes or additions to your codebase have not introduced new bugs or issues. It helps ensure that existing functionality continues to work as expected after modifications. In the context of assembly programming, regression testing can be performed by rerunning previously created test cases on the modified code. This helps identify any unintended side effects or regressions that may have been introduced. Automated testing frameworks can be particularly useful for regression testing, as they can easily rerun a large number of test cases and compare the results against expected outcomes. 8.2.4 Boundary testing. Boundary testing focuses on testing the behavior of your code at the boundaries of its input space. It aims to identify any issues that may arise when the input values are at the extreme ends of the acceptable range. In RISC-V assembly programming, boundary testing can involve creating test cases with input values that are at the minimum and maximum limits of the data types used in your code. For example, if you have a function that operates on integers, you can create test cases with the smallest and largest possible integer values. Boundary testing helps ensure that your code handles edge cases correctly and does not produce unexpected results or errors when the input values are at the limits of what is acceptable. 8.2.5 Stress testing. Stress testing involves testing your code under extreme or abnormal conditions to evaluate its performance and stability. It aims to identify any bottlenecks, performance issues, or potential failures that may occur when the code is subjected to high loads or unusual circumstances. In the context of RISC-V assembly programming, stress testing can involve creating test cases that put a heavy load on your code, such as executing a large number of instructions or performing complex calculations repeatedly. This helps identify any performance issues or limitations in your code. Stress testing can also involve testing your code with unusual or unexpected inputs to ensure that it handles them gracefully and does not crash or produce incorrect results. 8.2.6 Code Coverage Analysis. Code coverage analysis is a technique used to measure the extent to which your code is tested by your test cases. It helps identify areas of your code that are not adequately covered by your tests. In RISC-V assembly programming, code coverage analysis can be performed using specialized tools that track the execution of your code and identify which parts have been executed and which have not. This information can help you identify areas of your code that may require additional testing. By analyzing code coverage, you can ensure that your test cases exercise all parts of your code, including branches, loops, and conditional statements. This helps increase the confidence in the correctness of your code. Conclusion. Testing is a crucial aspect of assembly programming to ensure the correctness and reliability of your code. By employing various testing strategies such as unit testing, integration testing, regression testing, boundary testing, stress testing, and code coverage analysis, you can identify and fix issues in your code, improve its quality, and increase your confidence in its functionality. Remember that testing should be an ongoing process throughout the development cycle. Regularly testing your code and incorporating feedback from testing can help you catch and fix issues early, leading to more robust and reliable assembly programs. 8.3 Profiling and Performance Analysis. Profiling and performance analysis are essential techniques in optimizing and improving the efficiency of assembly programs. By identifying bottlenecks and areas of improvement, developers can make informed decisions to enhance the overall performance of their code. In this section, we will explore various profiling and performance analysis techniques specific to RISC-V assembly programming. 8.3.1 Profiling Tools. Profiling tools provide valuable insights into the runtime behavior of a program. They help identify areas of code that consume the most resources, such as CPU time or memory, allowing developers to focus their optimization efforts effectively. Here are some commonly used profiling tools for RISC-V assembly. 1. gprof. gprof is a popular profiling tool that comes bundled with the new compiler collection GCC. It provides statistical profiling information, including the number of times each function is called and the amount of time spent in each function. gprof can be used with RISC-V assembly programs by compiling them with GCC and enabling the profiling option. 2. perf. Perf is a powerful profiling tool that is part of the Linux kernel. It provides detailed information about CPU performance counters, cache misses, and other hardware events. Perf can be used to analyze the performance of RISC-V assembly programs running on Linux-based systems. 3. Valgrind. Valgrind is a dynamic binary instrumentation framework that can be used for profiling and debugging purposes. It provides tools like memcheck, which detects memory leaks and other memory-related errors, and calgrind, which performs cache simulation and instruction-level profiling. Valgrind can be used with RISC-V assembly programs by cross-compiling them for the Valgrind environment. 8.3.2 Performance Analysis Techniques. Once a profiling tool has been selected, various performance analysis techniques can be applied to identify and address performance bottlenecks. Here are some commonly used techniques for analyzing the performance of RISC-V assembly programs. 1. Code profiling. Code profiling involves analyzing the execution time of different sections of code to identify areas that consume the most CPU time. Profiling tools like gprof can generate detailed reports that highlight the functions or code blocks that contribute the most to the overall runtime. By focusing on optimizing these hotspots, developers can achieve significant performance improvements. 2. Memory profiling. Memory profiling involves analyzing the memory usage of a program to identify memory leaks, excessive memory allocations, or inefficient memory access patterns. Profiling tools like Valgrind's memcheck can detect memory-related errors, such as reading from uninitialized memory or accessing memory after it has been freed. By fixing these issues, developers can improve both the performance and stability of their RISC-V assembly programs. 3. Cache profiling. Cache profiling involves analyzing the cache behavior of a program to identify cache misses and optimize memory access patterns. Profiling tools like perf can provide detailed information about cache misses at different levels, L1, L2, etc., and help identify areas where cache optimizations can be applied. By reducing cache misses, developers can significantly improve the performance of their RISC-V assembly programs. 4. Instruction-level profiling. Instruction-level profiling involves analyzing the execution of individual instructions to identify performance bottlenecks at the instruction level. Profiling tools like Valgrind's calgrind can simulate cache behavior and provide detailed information about the number of instructions executed, cache hits and misses, and branch prediction accuracy. By analyzing this information, developers can identify instructions or code blocks that have a significant impact on performance and optimize them accordingly. 8.3.3 Optimization Techniques. Once performance bottlenecks have been identified through profiling and performance analysis, developers can apply various optimization techniques to improve the efficiency of their RISC-V assembly programs. Here are some commonly used optimization techniques. 1. Loop optimization. Loop optimization involves restructuring loops to minimize the number of instructions executed or reduce memory access overhead. Techniques like loop unrolling, loop fusion, and loop interchange can be applied to improve cache utilization and reduce branch mispredictions. 2. Data structure optimization. Data structure optimization involves choosing the most efficient data structures and algorithms for a given problem. By selecting data structures that minimize memory usage and optimize access patterns, developers can improve the overall performance of their RISC-V assembly programs. 3. Compiler optimization. Compiler optimization involves enabling compiler flags and options to generate more efficient code. Techniques like instruction scheduling, register allocation, and loop vectorization can be applied to optimize the generated assembly code. Understanding the impact of different compiler optimizations on RISC-V assembly programs is crucial for achieving optimal performance. 4. Algorithmic optimization. Algorithmic optimization involves analyzing the algorithm used in a program and identifying opportunities for improvement. By selecting or designing algorithms that have better time or space complexity, developers can achieve significant performance gains in their RISC-V assembly programs. In conclusion, profiling and performance analysis are crucial steps in optimizing RISC-V assembly programs. By using profiling tools and applying performance analysis techniques, developers can identify performance bottlenecks and apply optimization techniques to improve the efficiency of their code. Understanding the impact of different optimization techniques and selecting the most appropriate ones for a given problem is essential for achieving optimal performance in RISC-V assembly programming. 9. Introduction to RISC-V system calls. 9.1 What are system calls? In any operating system, there are certain tasks that can only be performed by the kernel, such as accessing hardware devices, managing memory, and handling input-output operations. These tasks are typically abstracted away from the user and application programs through a set of functions called system calls. A system call is a mechanism that allows user programs to request services from the operating system. It provides a way for user programs to interact with the kernel and access its functionalities. System calls act as an interface between user space and kernel space, allowing user programs to perform privileged operations that are otherwise restricted. System calls provide a standardized way for applications to perform common operations, such as reading from or writing to files, creating processes, allocating memory, and managing input-output devices. By using system calls, application developers can write portable code that can run on different operating systems without modification. The RISC-V architecture defines a set of system calls that are supported by the RISC-V operating system. These system calls are implemented by the kernel and can be invoked by user programs to perform various operations. The RISC-V system call interface follows a specific convention to ensure compatibility between different implementations of the RISC-V architecture. System calls are typically invoked using a special instruction called a system call instruction. In RISC-V, the system call instruction is called eCall. When a user program wants to make a system call, it sets the appropriate system call number in a designated register, usually a 0, and then executes the eCall instruction. The kernel then takes over and performs the requested operation on behalf of the user program. The system call number is used by the kernel to determine which system call the user program wants to invoke. Each system call is assigned a unique number, and the kernel uses this number to dispatch the request to the appropriate system call handler. The system call handler is a piece of code in the kernel that implements the functionality of the system call. The RISC-V system call convention specifies the registers that are used to pass arguments to the system call and the registers that are used to return values. The convention also defines how the system call number is passed to the kernel and how the kernel communicates the result of the system call back to the user program. System calls can be categorized into different types based on the functionality they provide. Some common types of system calls include file system operations, system calls for creating, opening, reading, writing, and closing files. These system calls provide the interface for file manipulation in the operating system. Process management, system calls for creating, terminating, and managing processes. These system calls allow user programs to control the execution of processes and manage their resources. Memory management, system calls for allocating and deallocating memory. These system calls provide the interface for dynamic memory allocation and deallocation in the operating system. Input-output operations, system calls for reading from and writing to input-output devices. These system calls allow user programs to interact with hardware devices such as keyboards, displays, and network interfaces. Communication, system calls for inter-process communication and synchronization. These system calls provide the means for processes to communicate and synchronize their activities. Understanding system calls is essential for writing low-level programs in RISC-V assembly. By leveraging system calls, you can access the full range of operating system functionalities and build more powerful and versatile applications. In the next section, we will explore the RISC-V system call convention in more detail and learn how to use system calls in RISC-V assembly programs. 9.2 RISC-V System Call Convention. The RISC-V System Call Convention defines the rules and conventions for making system calls in RISC-V assembly language programs. System calls are used to request services from the operating system, such as input-output operations, file access, and process management. Understanding the system call convention is essential for writing assembly programs that interact with the operating system. Register usage. In RISC-V, system calls are made using the eCall instruction. Before making a system call, the necessary arguments must be loaded into specific registers according to the convention. The arguments and return values are passed through specific registers as follows. The system call number is passed in register A7. The first argument is passed in register A0. The second argument is passed in register A1. The third argument is passed in register A2. The fourth argument is passed in register A3. Additional arguments can be passed in registers A4 to A7. The return value is stored in register A0. System call numbers. Each system call has a unique number associated with it. The system call number is used to identify the requested service. The specific system call numbers may vary depending on the operating system and the RISC-V implementation being used. It is important to consult the documentation or the system call interface provided by the operating system to determine the correct system call numbers. Making a system call. To make a system call in RISC-V assembly, the following steps are typically followed. Load the system call number into register A7. Load the arguments into the appropriate registers A0, A1, A2, etc. Execute the eCall instruction to trigger the system call. Retrieve the return value from register A0. Here is an example of making a system call to print a string using the right system call. Data. Message, ASCIIZ, hello, world. N, length, word 14. Text. La A0, message hash load the address of the string LWA1, length hash load the length of the string li A7, 64 hash system call number for write eCall hash make the system call. Hash the return value is stored in A0. In this example, the address of the string is loaded into register A0, the length of the string is loaded into register A1, and the system call number for write is loaded into register A7. The eCall instruction is then executed to trigger the system call. The return value, if any, will be stored in register A0. Error handling. System calls can fail for various reasons, such as invalid arguments or insufficient permissions. It is important to check the return value of a system call to determine if it was successful. A return value of -1 typically indicates an error, and the specific error code can be obtained by examining the value of the error global variable. Here is an example of making a system call and handling errors. Data. Message, ASCIIZ, hello, world. N, length, word 14. Text. La A0, message hash load the address of the string LWA1, length hash load the length of the string li A7, 64 hash system call number for write eCall hash make the system call. Hash check if the system call was successful bix A0, error hash branch to error label if A0 is 0. Hash system call was successful, continue execution. Error. Hash handle the error. In this example, the return value of the system call is checked using the bix instruction. If the return value, A0, is 0, indicating an error, the program branches to the error label to handle the error. Otherwise, the program continues execution. Conclusion. Understanding the RISC-V system call convention is crucial for writing assembly programs that interact with the operating system. By following the convention and using the appropriate system call numbers and registers, you can effectively make system calls and utilize the services provided by the operating system. Additionally, proper error handling ensures that your programs can gracefully handle any errors that may occur during system call execution. 9.3 Using system calls in assembly programs. System calls are an essential part of any operating system, allowing programs to interact with the underlying system and perform various tasks such as input-output operations, file management, and process control. In this section, we will explore how to use system calls in RISC-V assembly programs. Overview of system calls. A system call is a request made by a program to the operating system kernel for a specific service or resource. It provides an interface between user-level applications and the operating system, allowing programs to access privileged operations and services that are not available in user mode. In RISC-V, system calls are invoked using the eCall instruction. The eCall instruction transfers control to the operating system, which then performs the requested operation and returns control back to the program. The specific system call to be executed is determined by the value stored in the A7 register. System call convention. To use system calls in RISC-V assembly programs, we need to follow the system call convention. The convention specifies the registers that should be used to pass arguments to the system call and receive the return value. In RISC-V, the system call convention uses registers A0 to A7 to pass arguments to the system call. The return value of the system call is stored in register A0. Additional registers may be used for passing larger arguments or returning multiple values. The system call number is passed in register A7. Each system call has a unique number associated with it, which is defined by the operating system. The system call number determines the specific operation to be performed by the operating system. Example: printing a string. Let's consider an example of using a system call to print a string to the console. We will assume that the string is stored in memory starting at address str_adder and that the length of the string is stored in register A1. Data: str_adder, ASCIIZ, hello, world. N. Text: global_start_start. Hash load the address of the string into A0 la A0, str_adder. Hash load the length of the string into A1 li A1, 14. Hash set the system call number for printing a string li A7, 64. Hash invoke the system call ecall. Hash exit the program li A7, 93 li A0, 0 ecall. In this example, we first load the address of the string into register A0 using the load address instruction. We then load the length of the string into register A1 using the load immediate instruction. Next, we set the system call number for printing a string to 64, the value defined by the operating system. We then invoke the system call using the ecall instruction. After printing the string, we exit the program by setting the system call number for program termination to 93 and passing 0 as the exit status. Common system calls. RISC-V provides a set of common system calls that are supported by most operating systems. These system calls include operations such as file management, process control, memory allocation, and input-output operations. Some of the common system calls in RISC-V include: open, opens a file for reading or writing. Read, reads data from a file. Write, writes data to a file. Close, closes a file. Exit, terminates the program. BRK, changes the program's data segment size. SBRK, allocates memory dynamically. Fork, creates a new process. Execv, executes a new program. Wait, waits for a child process to terminate. The specific system calls and their corresponding numbers may vary depending on the operating system being used. It is important to consult the documentation or reference manual of the specific operating system to determine the available system calls and their usage. In conclusion, system calls are a crucial aspect of RISC-V assembly programming as they allow programs to interact with the underlying operating system and perform various tasks. By following the system call convention and using the ecall instruction, we can effectively utilize system calls in our assembly programs. Understanding the available system calls and their usage is essential for developing robust and functional RISC-V assembly programs. 9.4 Common system calls. System calls are an essential part of any operating system, including RISC-V. They provide a way for user programs to interact with the underlying operating system and access various services and resources. In this section, we will explore some of the common system calls available in RISC-V assembly. 9.4.1 Print string. One of the most basic system calls is the ability to print a string to the console. In RISC-V assembly, this can be achieved using the li instruction to load the system call number into register A7 and the string address into register A0. The system call number for printing a string is typically 4. Here is an example of how to print a string using the ecall instruction. Data. Message, ASCIIZ, hello, world. Text. La A0, message li A7, 4 ecall. In this example, the string, hello, world, is stored in the data section, and its address is loaded into register A0 using the la instruction. The system call number 4 is loaded into register A7 using the li instruction. Finally, the ecall instruction is used to invoke the system call. 9.4.2 Read integer. Another common system call is reading an integer from the user. This can be useful when writing programs that require user input. In RISC-V assembly, the system call number for reading an integer is typically 5. Here is an example of how to read an integer using the ecall instruction. Li A7, 5 ecall. After executing this code, the user will be prompted to enter an integer value. The entered value will be stored in register A0, which can then be used by the program for further processing. 9.4.3 Exit program. Exiting a program is another common operation that can be achieved using a system call. In RISC-V assembly, the system call number for program exit is typically 10. The exit status can be passed as an argument in register A0. Here is an example of how to exit a program using the ecall instruction. Li A0, 0 li A7, 10 ecall. In this example, the exit status is set to 0 using the li instruction and loaded into register A0. The system call number 10 is loaded into register A7. Finally, the ecall instruction is used to invoke the system call and terminate the program. 9.4.4 File operations. RISC-V Assembly also provides system calls for performing file operations, such as opening, reading, writing, and closing files. These system calls allow programs to interact with files stored on the file system. The system call numbers for file operations vary depending on the specific operation. For example, the system call number for opening a file is typically 1024, while the system call number for reading from a file is 1025. Here is an example of how to open a file using the eCall instruction. Li A0, filename Li A1, 0 Li A2, 0 Li A7, 1024 eCall. In this example, the filename is stored in register A0, and the file access mode is set to 0, read only. The system call number 1024 is loaded into register A7. After executing this code, the file will be opened, and its file descriptor will be returned in register A0. 9.4.5 Memory Allocation. Dynamic memory allocation is a common requirement in many programs. RISC-V Assembly provides system calls for allocating and freeing memory dynamically. The system call number for memory allocation is typically 9. The size of the memory block to be allocated can be passed as an argument in register A0, and the address of the allocated memory block will be returned in register A0. Here is an example of how to allocate memory using the eCall instruction. Li A0, size Li A7, 9 eCall. In this example, the size of the memory block to be allocated is stored in register A0. The system call number 9 is loaded into register A7. After executing this code, the address of the allocated memory block will be returned in register A0. These are just a few examples of the common system calls available in RISC-V Assembly. System calls provide a powerful mechanism for interacting with the operating system and accessing various services and resources. By understanding and utilizing these system calls, you can write more versatile and functional programs in RISC-V Assembly. 10. Interrupts and exceptions in RISC-V. 10.1 Interrupts and exceptions overview. In any computer system, interrupts and exceptions play a crucial role in handling unexpected events and ensuring the system's stability and reliability. RISC-V architecture provides a comprehensive mechanism for managing interrupts and exceptions efficiently. This section will provide an overview of interrupts and exceptions in RISC-V and their significance in the overall system operation. What are interrupts and exceptions? Interrupts and exceptions are events that occur during the execution of a program, causing the normal flow of instructions to be temporarily suspended. These events can be triggered by both internal and external factors. Interrupts are typically caused by external devices, such as timers, input-output devices, or hardware interrupts, while exceptions are generated by the processor itself in response to specific conditions, such as arithmetic errors or illegal instructions. Interrupts and exceptions are essential for handling time-sensitive tasks, managing input-output operations, and ensuring the system's overall stability. By temporarily interrupting the normal program execution, interrupts and exceptions allow the processor to respond to critical events promptly. Interrupts and exceptions in RISC-V. RISC-V architecture provides a well-defined mechanism for handling interrupts and exceptions. It includes a set of interrupt and exception handling instructions, a dedicated interrupt vector table, and a set of registers to manage the interrupt and exception context. RISC-V supports two types of interrupts: external interrupts and software interrupts. External interrupts are generated by external devices and are typically used for input-output operations or to signal time-sensitive events. Software interrupts, also known as traps, are triggered by specific instructions and are used for system calls or to handle exceptional conditions. Exceptions in RISC-V are categorized into three types: synchronous exceptions, asynchronous exceptions, and traps. Synchronous exceptions occur as a result of executing specific instructions, such as arithmetic errors or illegal instructions. Asynchronous exceptions are caused by external events, such as hardware faults or interrupts. Traps are software-generated exceptions used for system calls or to handle exceptional conditions. Interrupt and exception handling process. When an interrupt or exception occurs, the processor follows a specific sequence of steps to handle the event effectively. The interrupt and exception handling process typically involves the following steps. Interrupt exception detection. The processor detects the occurrence of an interrupt or exception event. This can be triggered by external devices, specific instructions, or other exceptional conditions. Interrupt exception acknowledgement. The processor acknowledges the interrupt or exception event and saves the current program state, including the program counter PC and other relevant registers. Interrupt exception dispatch. The processor determines the appropriate interrupt or exception handler based on the type of event. It uses the interrupt vector table to locate the handler's address. Interrupt exception handling. The processor transfers control to the interrupt or exception handler routine. The handler performs the necessary operations to handle the event, such as saving the current context, executing specific instructions, or interacting with external devices. Interrupt exception return. Once the interrupt or exception handling is complete, the processor restores the saved context and resumes the interrupted program execution. This involves restoring the program counter, PC, and other relevant registers. Interrupt and exception vector table. The interrupt and exception vector table is a data structure used by the processor to determine the appropriate interrupt or exception handler based on the event type. It contains a list of addresses corresponding to different interrupt or exception handlers. In RISC-V, the interrupt and exception vector table is typically located at a fixed memory address. Each entry in the table corresponds to a specific interrupt or exception event and contains the address of the corresponding handler routine. During the interrupt or exception handling process, the processor uses the events caused to index into the vector table and retrieve the appropriate handler's address. This allows for efficient and direct dispatching of interrupts and exceptions. Conclusion. Interrupts and exceptions are critical components of any computer system, allowing for the handling of unexpected events and ensuring the system's stability and reliability. RISC-V architecture provides a comprehensive mechanism for managing interrupts and exceptions efficiently. This section provided an overview of interrupts and exceptions in RISC-V, their types, and the general handling process. Understanding interrupts and exceptions is essential for developing robust and reliable RISC-V assembly programs. 10.2 Interrupt and exception handling in assembly. Interrupts and exceptions are crucial aspects of any computer system, including RISC-V. They allow the processor to respond to external events or internal conditions that require immediate attention. In this section, we will explore how interrupts and exceptions are handled in RISC-V assembly language. Interrupts and exceptions overview. Interrupts and exceptions are events that can occur during the execution of a program, causing the normal flow of execution to be temporarily suspended. They can be triggered by various sources, such as hardware devices, software conditions, or errors. Interrupts are typically used for external events, while exceptions are used for internal conditions. Interrupts and exceptions are classified into different types based on their priority and the actions they require. Some common types include timer interrupt. This interrupt is triggered by a hardware timer and is used for timekeeping or scheduling purposes. External interrupt. This interrupt is triggered by an external device, such as a keyboard or mouse, to signal the processor that it requires attention. Software interrupt. This interrupt is triggered by a software instruction, allowing the program to request a specific service from the operating system. Exception. Exceptions are triggered by exceptional conditions, such as arithmetic errors, page faults, or illegal instructions. Handling interrupts and exceptions. When an interrupt or exception occurs, the processor needs to handle it appropriately to ensure the system's stability and reliability. In RISC-V assembly language, interrupt and exception handling involves the following steps. Saving the current context. Before handling the interrupt or exception, the processor needs to save the current context, including the program counter PC and other relevant registers. This allows the system to resume execution from the same point once the interrupt or exception is handled. Switching to the interrupt/exception handler. After saving the context, the processor switches to the interrupt or exception handler routine. This routine is a specific section of code that is responsible for handling the interrupt or exception. The handler routine may be predefined by the system or written by the programmer. Handling the interrupt/exception. Inside the handler routine, the necessary actions are taken to address the interrupt or exception. This may involve servicing the external device, resolving the exceptional condition, or performing any other required tasks. The handler routine should be designed to handle the specific interrupt or exception type. Restoring the context. Once the interrupt or exception has been handled, the processor restores the saved context, including the program counter and other registers. This allows the system to resume execution from the point where it was interrupted. Returning to the interrupted program. After restoring the context, the processor returns to the interrupted program and continues its execution from the point where it was interrupted. The program can now proceed as if the interrupt or exception never occurred. Writing interrupt and exception handlers. In RISC-V assembly language, interrupt and exception handlers are written as separate sections of code that are linked to the main program. These handlers are typically defined using specific labels and are placed in a specific location in memory known as the interrupt or exception vector table. The interrupt or exception vector table is a data structure that contains the addresses of the corresponding interrupt or exception handlers. When an interrupt or exception occurs, the processor uses the vector table to determine the address of the appropriate handler and jumps to it. To write an interrupt or exception handler, you need to follow these steps. Define the handler label. Start by defining a label for the handler routine. This label will be used to reference the handler in the interrupt or exception vector table. Save the context. Inside the handler routine, save the necessary registers and the program counter PC to preserve the current context. This can be done using the SW instruction to store the register values in memory. Handle the interrupt exception. Write the code to handle the specific interrupt or exception. This may involve interacting with hardware devices, performing calculations, or resolving exceptional conditions. Restore the context. After handling the interrupt or exception, restore the saved context by loading the register values in the program counter PC from memory. Return from the handler. Use the junior instruction to return from the handler routine and resume execution of the interrupted program. Conclusion. Interrupts and exceptions play a vital role in the proper functioning of a RISC-V system. Understanding how to handle interrupts and exceptions in assembly language is essential for developing robust and reliable software. By following the steps outlined in this section, you can effectively handle interrupts and exceptions in your RISC-V assembly programs. 10.3 Interrupt and Exception Handlers. In RISC-V, interrupts and exceptions are events that can occur during the execution of a program and require special handling. Interrupts are external events that can pause the normal execution of a program, while exceptions are internal events that occur due to certain conditions or instructions. To handle these events, RISC-V provides a mechanism called interrupt and exception handlers. Interrupt handlers. Interrupt handlers are routines that are executed when an interrupt occurs. They are responsible for handling the interrupt and performing any necessary actions. In RISC-V, interrupts can be triggered by various sources such as timers, external devices, or software interrupts. When an interrupt occurs, the processor suspends the execution of the current program and transfers control to the interrupt handler. The interrupt handler then performs the required tasks, such as saving the context of the interrupted program, handling the interrupt request, and restoring the context before returning to the interrupted program. To implement an interrupt handler in RISC-V assembly, you need to follow these steps. Disable interrupts. Before entering the interrupt handler, it is important to disable interrupts to prevent nested interrupts from occurring. This can be done by clearing the interrupt enable bit in the status register. Save the context. The interrupt handler should save the context of the interrupted program, including the values of registers and any other necessary state information. This is important to ensure that the interrupted program can resume execution correctly after the interrupt is handled. Handle the interrupt. The interrupt handler performs the necessary actions to handle the interrupt. This may involve reading data from an external device, updating system variables, or performing any other required operations. Restore the context. After handling the interrupt handler restores the saved context of the interrupted program. This includes restoring the values of registers and any other state information that was saved. Enable interrupts. Finally, the interrupt handler enables interrupts again by setting the interrupt enable bit in the status register. This allows other interrupts to be processed if they occur. Exception handlers. Exception handlers are similar to interrupt handlers, but they are triggered by internal events rather than external interrupts. Exceptions can occur due to various reasons, such as invalid instructions, arithmetic errors, or page faults in memory access. When an exception occurs, the processor transfers control to the exception handler, which is responsible for handling the exception and taking appropriate actions. The exception handler performs tasks such as saving the context, handling the exception condition, and restoring the context before returning to the interrupted program. To implement an exception handler in RISC-V assembly, you need to follow similar steps as for interrupt handlers. Disable exceptions. Before entering the exception handler, it is important to disable exceptions to prevent nested exceptions from occurring. This can be done by clearing the exception enable bit in the status register. Save the context. The exception handler should save the context of the interrupted program, including the values of registers and any other necessary state information. Handle the exception. The exception handler performs the necessary actions to handle the exception. This may involve error handling, exception-specific operations, or any other required tasks. Restore the context. After handling the exception handler restores the saved context of the interrupted program. Enable exceptions. Finally, the exception handler enables exceptions again by setting the exception enable bit in the status register. Exception and interrupt vector table. In RISC-V, the addresses of interrupt and exception handlers are stored in a special data structure called the interrupt and exception vector table. This table contains the addresses of all the interrupt and exception handlers in the system. When an interrupt or exception occurs, the processor uses the interrupt or exception number to index into the vector table and fetch the corresponding handler's address. The processor then transfers control to the handler by jumping to the fetched address. The vector table is typically located at a fixed address in memory, and the addresses of the handlers are stored in a sequential manner. The table is initialized during system startup or initialization, and the addresses of the handlers are set accordingly. In summary, interrupt and exception handlers are essential for handling interrupts and exceptions in RISC-V assembly. They allow the system to respond to external events and internal exceptions in a controlled and predictable manner. By following the steps outlined above and utilizing the interrupt and exception vector table, you can effectively handle interrupts and exceptions in your RISC-V assembly programs. 10.4 Interrupt and Exception Vector Table. In RISC-V, interrupts and exceptions are events that can occur during the execution of a program and require special handling. These events can be triggered by external devices, such as timers or input-output devices, or by internal conditions, such as arithmetic overflow or illegal instructions. When an interrupt or exception occurs, the processor needs to transfer control to a specific handler routine to handle the event appropriately. The interrupt and exception vector table is a data structure that maps each interrupt or exception to its corresponding handler routine. It is typically located in a fixed memory location and is initialized during system startup. When an interrupt or exception occurs, the processor uses the vector table to determine the address of the handler routine and transfers control to it. The vector table is organized as an array of addresses, where each entry corresponds to a specific interrupt or exception. The index of each entry in the array represents the interrupt or exception number. For example, if the interrupt number is 3, the corresponding entry in the vector table will be at index 3. The vector table is usually implemented as a read-only memory, ROM, or a portion of the memory that is not writable by the user program. This ensures that the vector table remains intact and cannot be modified by the user program. By separating the vector table from the user program's memory space, the system can ensure that the interrupt and exception handling routines are always available and can be executed without interference. During system startup, the vector table is initialized with the addresses of the corresponding interrupt and exception handler routines. These handler routines are responsible for handling the specific interrupt or exception and performing any necessary actions, such as saving the processor state, servicing the interrupt, or handling the exception condition. To handle an interrupt or exception, the processor follows a specific sequence of steps. When an interrupt or exception occurs, the processor first saves the current state of the program, including the program counter PC and other relevant registers, onto the stack. This allows the handler routine to resume execution from the point where the interrupt or exception occurred once it has finished handling the event. The processor then looks up the address of the handler routine in the vector table using the interrupt or exception number. It retrieves the address from the corresponding entry in the vector table. The processor transfers control to the handler routine by setting the program counter PC to the address of the handler routine. This causes the processor to start executing instructions from the handler routine. The handler routine performs the necessary actions to handle the interrupt or exception. This may involve servicing the interrupt, handling the exception condition, or performing any other required operations. Once the handler routine has finished handling the interrupt or exception, it restores the saved state from the stack, including the program counter PC and other relevant registers. This allows the interrupted program to resume execution from the point where it was interrupted. By using the interrupt and exception vector table, the system can provide a flexible and efficient mechanism for handling interrupts and exceptions in RISC-V. The vector table allows the system to easily map each interrupt or exception to its corresponding handler routine, ensuring that the appropriate actions are taken when these events occur. It is important to note that the specific implementation of the interrupt and exception vector table may vary depending on the RISC-V processor and the system design. The exact memory location and format of the vector table may differ between different systems. Therefore, it is essential to consult the processor's documentation and the system specifications to determine the exact details of the vector table implementation for a particular system. In conclusion, the interrupt and exception vector table is a crucial component of the RISC-V system that enables efficient handling of interrupts and exceptions. By mapping each interrupt or exception to its corresponding handler routine, the vector table ensures that the system can respond appropriately to these events and maintain the integrity and stability of the system's operation. 11. Advanced topics in RISC-V Assembly. 11.1 Floating point arithmetic. Floating point arithmetic is a fundamental aspect of modern computing that allows for the representation and manipulation of real numbers in a computer system. In RISC-V Assembly, floating point arithmetic is supported through the use of the floating point extension RV32F and RV64F, or the double precision floating point extension RV32D and RV64D depending on the specific implementation. Floating point representation. Before diving into the details of floating point arithmetic in RISC-V Assembly, it is important to understand how real numbers are represented in a computer system. Unlike integers, which can be represented exactly using a fixed number of bits, real numbers require a more complex representation due to their infinite precision. The most common representation for floating point numbers is the IEEE 754 standard, which defines formats for both single precision 32-bit and double precision 64-bit floating point numbers. In RISC-V Assembly, the floating point registers F0, F31 are used to store and manipulate floating point values. Floating point instructions. RISC-V provides a set of instructions specifically designed for performing floating point arithmetic operations. These instructions operate on the floating point registers and allow for various operations such as addition, subtraction, multiplication, division, and more. The floating point arithmetic instructions in RISC-V Assembly are similar to their integer counterparts, but with a prefix, f, to indicate that they operate on floating point values. For example, the add s instruction is used to add two single precision floating point numbers, while the add d instruction is used to add two double precision floating point numbers. Here are some examples of floating point arithmetic instructions in RISC-V Assembly. Add SF1, F2, F3 adds the values in F2 and F3 and stores the result in F1. Sub df4, F5, F6 subtracts the value in F6 from F5 and stores the result in F4. Mul, SF7, F8, F9 multiplies the values in F8 and F9 and stores the result in F7. Div, df10, F11, F12 divides the value in F11 by F12 and stores the result in F10. Floating point conversions. In addition to arithmetic operations, RISC-V Assembly also provides instructions for converting between floating point and integer representations. These instructions are useful when working with mixed data types or when performing operations that require conversions between different representations. The CVT S W instruction is used to convert a 32-bit signed integer to a single precision floating point number, while the CVT W S instruction is used to convert a single precision floating point number to a 32-bit signed integer. Similarly, the CVT D W instruction converts a 32-bit signed integer to a double precision floating point number, and the CVT W D instruction converts a double precision floating point number to a 32-bit signed integer. Here are some examples of floating point conversion instructions in RISC-V assembly. CVT S WF13 A0 converts the value in register A0 32-bit signed integer to a single precision floating point number and stores the result in F13. CVT W SA1 F14 converts the value in register F14 single precision floating point number to a 32-bit signed integer and stores the result in A1. CVT D WF15 A2 converts the value in register A2 32-bit signed integer to a double precision floating point number and stores the result in F15. CVT W DA3 F16 converts the value in register F16 double precision floating point number to a 32-bit signed integer and stores the result in A3. Exception handling. Floating point arithmetic in RISC-V assembly also involves handling exceptions that may occur during the execution of floating point instructions. These exceptions include overflow, underflow, invalid operation, and divide by zero. When an exception occurs, the floating point status flags are set accordingly, and the program can handle the exception by branching to an exception handler. RISC-V provides instructions such as FCSR to read and write the floating point control and status register, which contains information about the current state of the floating point unit. Summary. Floating point arithmetic is an essential aspect of modern computing, allowing for the representation and manipulation of real numbers in a computer system. In RISC-V assembly, floating point arithmetic is supported through the floating point extension or the double precision floating point extension, depending on the specific implementation. RISC-V provides a set of instructions for performing floating point arithmetic operations, as well as instructions for converting between floating point and integer representations. Exception handling is also an important aspect of floating point arithmetic in RISC-V assembly, allowing programs to handle exceptions that may occur during the execution of floating point instructions. 11.2 Vector instructions. Vector instructions are a powerful feature of the RISC-V architecture that allow for efficient processing of large sets of data in parallel. These instructions operate on vectors, which are contiguous arrays of data elements. By performing the same operation on multiple elements simultaneously, vector instructions can greatly accelerate certain types of computations, such as multimedia processing, scientific simulations, and data analytics. Vector registers. In RISC-V, vector registers are used to hold the data elements of a vector. These registers are distinct from the general-purpose registers used for scalar operations. Vector registers are wider than scalar registers, allowing them to hold multiple data elements. The number of elements that can be stored in a vector register depends on the specific implementation of the RISC-V architecture. Vector registers are denoted by the prefix v, followed by a number, such as v0, v1, v2, and so on. Each vector register can hold a fixed number of data elements, which are typically of the same size. For example, a vector register may be able to hold 8 single precision floating point numbers or 16 8-bit integers. Vector instructions. RISC-V provides a set of vector instructions that operate on vector registers. These instructions are designed to perform the same operation on multiple elements of a vector simultaneously. They can be used to perform arithmetic, logical, and other operations on vectors efficiently. Vector instructions in RISC-V are typically denoted by the v prefix followed by the mnemonic of the operation, such as VAD vector addition, VSUB vector subtraction, VMUL vector multiplication, and VDIV vector division. The operands of these instructions are vector registers, and the result is stored in another vector register. For example, the VAD instruction adds the corresponding elements of 2 vector registers and stores the result in a third vector register. Similarly, the VMUL instruction multiplies the corresponding elements of 2 vector registers and stores the result in a third vector register. Vector length. The length of a vector is the number of elements it contains. The length of a vector can be specified explicitly in vector instructions or determined implicitly by the hardware. The length of a vector determines the number of elements that can be processed in parallel. RISC-V supports fixed-length vectors, where the length is determined at compile time, and scalable vectors, where the length can be dynamically adjusted at runtime. Fixed-length vectors are useful when the number of elements to be processed is known in advance, while scalable vectors provide flexibility in handling vectors of varying lengths. Vectorization. Vectorization is the process of rewriting scalar code to use vector instructions. It involves identifying loops or sections of code that can be parallelized and replacing scalar operations with vector operations. Vectorization can significantly improve the performance of certain algorithms by exploiting the parallelism inherent in vector instructions. To vectorize code, the programmer needs to understand the data dependencies in the available vector instructions. The code must be structured in a way that allows for efficient vectorization. In some cases, the compiler may be able to automatically vectorize code, but but manual vectorization often yields better results. Vectorization examples. Let's consider a simple example to illustrate the concept of vectorization. Suppose we have two arrays, A and B, each containing 8 single precision floating point numbers. We want to compute the element-wise sum of the two arrays and store the result in a third array, C. In scalar code, we would use a loop to iterate over the elements of the arrays and perform the addition operation one element at a time. However, by using vector instructions, we can perform the addition operation on multiple elements simultaneously. Here's an example of how the code can be vectorized using RISC-V vector instructions. Hash scalar code for I in range 8. C I equals A I plus B I. Hash vectorized code. For I in range 0, 8, vector underscore length. VA equals float A, I VB equals float B, I VC equals VAD, VA, VB VStore C, I, VC. In the vectorized code, the float instruction is used to load a vector of elements from the arrays A and B. The VAD instruction performs the element-wise addition, and the VStore instruction stores the result in the array C. By using vector instructions, we can process multiple elements in parallel, resulting in faster execution compared to the scalar code. Conclusion. Vector instructions are a powerful feature of the RISC-V architecture that enable efficient processing of large sets of data in parallel. By performing the same operation on multiple elements simultaneously, vector instructions can greatly accelerate certain types of computations. Understanding vector instructions and how to vectorize code can lead to significant performance improvements in RISC-V assembly programming. 11.3 Multithreading and parallel processing. Multithreading and parallel processing are advanced topics in computer architecture that allow for improved performance and efficiency in executing tasks. In the context of RISC-V assembly, multithreading refers to the ability of a processor to execute multiple threads concurrently, while parallel processing involves the simultaneous execution of multiple instructions or tasks. Multithreading. Multithreading is a technique that allows a processor to execute multiple threads concurrently. A thread is a sequence of instructions that can be scheduled and executed independently. By utilizing multithreading, a processor can overlap the execution of multiple threads, thereby improving overall performance. In RISC-V assembly, multithreading can be achieved through the use of multiple hardware threads or through software-based thread scheduling. Hardware multithreading involves the use of multiple physical cores, each capable of executing its own thread. This approach provides true parallelism, as each core can execute instructions simultaneously. Software-based multithreading, on the other hand, involves time-sharing the execution of threads on a single core. This approach allows for the illusion of concurrent execution by rapidly switching between threads. To implement multithreading in RISC-V assembly, the processor must support the necessary instructions and mechanisms for thread management. This typically includes instructions for thread creation, synchronization, and context switching. Additionally, the operating system or runtime environment must provide the necessary infrastructure for managing threads and scheduling their execution. Multithreading can provide several benefits in RISC-V assembly programming. It can improve overall system throughput by allowing the processor to execute multiple threads simultaneously. It can also enhance responsiveness by enabling concurrent execution of tasks, such as handling user input while performing background computations. Furthermore, multithreading can facilitate efficient utilization of system resources, as idle cores can be utilized for executing other threads. Parallel processing. Parallel processing involves the simultaneous execution of multiple instructions or tasks to achieve improved performance. It can be achieved through various techniques, such as instruction-level parallelism, ILP, and data-level parallelism, DLP. In RISC-V assembly, parallel processing can be achieved through the use of vector instructions. Vector instructions allow for the simultaneous execution of the same operation on multiple data elements, known as a vector. These instructions operate on vector registers, which can hold multiple data elements. By utilizing vector instructions, a processor can perform computations on multiple data elements in parallel, thereby achieving significant performance improvements. To utilize parallel processing in RISC-V assembly, programmers need to identify opportunities for vectorization. This involves identifying computations that can be performed on multiple data elements simultaneously. Once identified, the programmer can rewrite the code to utilize vector instructions and vector registers. The compiler or assembler can also assist in automatically vectorizing code by recognizing patterns and generating vector instructions. Parallel processing can provide substantial performance benefits in RISC-V assembly programming. By executing multiple instructions in parallel, the overall execution time of a program can be significantly reduced. This is particularly beneficial for computationally intensive tasks, such as image processing, numerical simulations, and scientific computations. Additionally, parallel processing can also lead to energy efficiency improvements, as the execution of multiple instructions can be completed in fewer clock cycles. Multithreading and parallel processing in combination. Multithreading and parallel processing can be combined to further enhance performance and efficiency in RISC-V assembly programming. By utilizing both techniques, a processor can achieve concurrent execution of multiple threads while also performing parallel computations on each thread. This combination can be particularly beneficial in scenarios where both task-level parallelism and data-level parallelism exist. For example, in a scientific simulation, multiple threads can be used to simulate different parts of the system concurrently, while vector instructions can be used within each thread to perform computations on multiple data elements simultaneously. However, it is important to note that the effectiveness of combining multithreading and parallel processing depends on various factors, such as the nature of the workload, the available hardware resources, and the efficiency of the thread and vectorization implementations. Careful consideration and analysis are required to determine the optimal approach for a given scenario. In conclusion, multithreading and parallel processing are advanced techniques that can significantly improve performance and efficiency in RISC-V assembly programming. Multithreading allows for concurrent execution of multiple threads, while parallel processing enables the simultaneous execution of multiple instructions or tasks. By combining these techniques, programmers can achieve even greater performance gains. However, it is important to carefully analyze the workload and consider the available hardware resources to determine the most effective approach. 11.4 Security and Privilege Levels. Security and privilege levels are important concepts in computer systems that help ensure the safety and integrity of data and resources. In the context of RISC-V assembly, security and privilege levels refer to the different levels of access and control that different parts of the system have. Understanding privilege levels. RISC-V defines 3 privilege levels: machine mode M mode, supervisor mode S mode, and user mode U mode. Each privilege level has its own set of instructions and capabilities, with higher privilege levels having more control and access to system resources. Machine mode M mode. This is the highest privilege level in RISC-V. It is typically reserved for the operating system kernel and firmware. M mode has full control over the system and can execute privileged instructions, access all memory, and configure system-level settings. Supervisor mode S mode. S mode is the next level of privilege below M mode. It is designed for the operating system supervisor or hypervisor. S mode has restricted access compared to M mode but still has control over system resources and can execute privileged instructions. User mode U mode. U mode is the lowest privilege level in RISC-V. It is intended for user applications and provides the least amount of control and access to system resources. U mode cannot execute privileged instructions or directly access certain system resources. Privilege levels and security. The privilege levels in RISC-V assembly play a crucial role in ensuring system security. By restricting access to certain instructions and resources, privilege levels help prevent unauthorized access and protect sensitive data. Isolation. Privilege levels provide isolation between different parts of the system. User applications running in U mode are isolated from the operating system and other applications running in S mode or M mode. This isolation prevents unauthorized access and interference between different components. Memory protection. Privilege levels enable memory protection mechanisms. The operating system running in S mode can set up memory regions and access permissions for user applications in U mode. This prevents user applications from accessing or modifying memory that they should not have access to. System call interface. Privilege levels define the system call interface, which allows user applications to request services from the operating system. User applications in U mode can only invoke a limited set of system calls, while the operating system in S mode has access to a broader range of system calls. This controlled interface ensures that user applications cannot directly manipulate system resources without going through the appropriate channels. Changing privilege levels. RISC-V provides instructions to change privilege levels, allowing the system to transition between different modes as needed. These instructions are known as privilege level change instructions or privilege level traps. MRET. The MRET instruction is used to return from a trap or exception handler in M mode. It restores the privilege level and program counter to the values before the trap occurred. SRET. The SRET instruction is similar to MRET but is used in S mode. It returns from a trap or exception handler in S mode and restores the privilege level and program counter. URET. The URET instruction is used to return from a trap or exception handler in U mode. It restores the privilege level and program counter to the values before the trap occurred. These instructions allow the system to transition between different privilege levels, ensuring that the appropriate level of access and control is maintained. Security extensions. RISC-V also provides security extensions that enhance the security features of the architecture. These extensions include additional instructions and features that can be used to implement security-related functionality. Physical Memory Protection (PMP). The PMP extension provides fine-grained memory protection by allowing the definition of memory regions and access permissions. It enables the system to protect critical memory regions from unauthorized access. Trap and interrupt handling. RISC-V provides mechanisms for handling traps and interrupts at different privilege levels. These mechanisms allow the system to respond to events such as exceptions, interrupts, and system calls in a controlled manner. Virtualization. RISC-V includes virtualization extensions that enable the execution of multiple virtual machines on a single physical machine. These extensions provide isolation between virtual machines and allow for secure execution of guest operating systems. By incorporating these security extensions, RISC-V provides a flexible and secure platform for a wide range of applications, from embedded systems to cloud computing. Conclusion. Security and privilege levels are essential aspects of RISC-V assembly programming. Understanding how privilege levels work and how they can be changed is crucial for building secure and reliable systems. By leveraging the privilege levels and security extensions provided by RISC-V, developers can ensure the integrity and safety of their applications and data. 12. Building real-world applications with RISC-V Assembly. 12.1 Embedded Systems Programming. Embedded systems are computer systems designed to perform specific tasks within larger systems. They are typically small, low-power devices that are integrated into various applications such as consumer electronics, automotive systems, medical devices, and industrial control systems. Embedded systems programming involves writing software that runs on these devices, controlling their hardware and performing the desired functions. RISC-V assembly language is well suited for embedded systems programming due to its simplicity, efficiency, and flexibility. In this section, we will explore the key concepts and techniques involved in developing embedded systems using RISC-V assembly. Understanding embedded systems. Embedded systems are designed to perform specific tasks with real-time constraints. They often have limited resources such as memory, processing power, and energy. As an embedded systems programmer, it is crucial to understand the hardware architecture and constraints of the target device. RISC-V assembly provides a low-level interface to the hardware, allowing precise control over the system's resources. By directly manipulating registers, memory, and I/O devices, you can optimize the performance and efficiency of your embedded system. Hardware interfacing. Embedded systems often require interaction with external hardware devices such as sensors, actuators, and communication interfaces. RISC-V assembly provides instructions and techniques to interface with these devices. For example, you can use load and store instructions to read from and write to memory-mapped I/O registers. These registers control the behavior of peripheral devices and allow you to exchange data with them. By understanding the device's datasheet and the memory-mapped register layout, you can effectively communicate with the hardware. Interrupt handling. Interrupts are crucial in embedded systems as they allow the system to respond to external events in a timely manner. RISC-V assembly provides instructions and mechanisms to handle interrupts efficiently. When an interrupt occurs, the processor suspends the current execution and transfers control to an interrupt handler routine. The handler performs the necessary actions to handle the interrupt and then returns control to the interrupted program. In RISC-V assembly, you can define interrupt handlers using the eCall instruction and the MRET instruction to return from the interrupt handler. By properly configuring the interrupt controller and prioritizing interrupts, you can ensure that critical events are handled promptly. Power management. Power consumption is a critical consideration in embedded systems, especially for battery-powered devices. RISC-V assembly allows you to optimize power consumption by controlling the system's power modes and managing clock frequencies. You can use instructions such as WFI, wait for interrupt, to put the processor into a low-power sleep mode until an interrupt occurs. Additionally, you can adjust the clock frequency dynamically based on the system's workload to save power. Real-time programming. Many embedded systems have real-time requirements, where tasks must be completed within specific time constraints. RISC-V assembly provides the necessary tools to meet these real-time requirements. By understanding the timing characteristics of your system, you can use instructions such as RD cycle and RD time to measure the execution time of critical sections of code. This information can be used to ensure that tasks are completed within their deadlines and to optimize the system's performance. Debugging and testing. Embedded systems programming often involves debugging and testing on the target hardware. RISC-V assembly provides debugging features such as breakpoints, watch points, and trace capabilities to aid in the debugging process. You can use a debugger, such as OpenOCD or GDB, to connect to the target device and step through the assembly code, inspect registers, and memory contents. Additionally, you can use software and hardware tools to simulate and test your embedded system before deploying it on the actual hardware. Conclusion. Embedded systems programming with RISC-V assembly offers a powerful and efficient way to develop applications for a wide range of devices. By understanding the hardware architecture, interfacing with external devices, handling interrupts, managing power, meeting real-time requirements, and debugging effectively, you can build robust and optimized embedded systems. In the next section, we will explore the exciting world of operating system development using RISC-V assembly. 12.2 Operating System Development. Operating system development is a complex and challenging task that requires a deep understanding of computer architecture and low-level programming. In this section, we will explore the fundamentals of operating system development using RISC-V assembly language. Understanding operating systems. An operating system, OS, is a software that manages computer hardware and software resources and provides common services for computer programs. It acts as an intermediary between the hardware and the user applications, enabling the efficient and secure execution of programs. Operating systems perform various essential functions, including process management, memory management, file system management, device management, and user interface management. These functions are implemented through a combination of hardware and software components. RISC-V assembly in operating system development. RISC-V assembly language is well suited for operating system development due to its simplicity, modularity, and extensibility. The RISC-V ISA provides a clean and orthogonal instruction set architecture, making it easier to implement the low-level functionality required by an operating system. Operating system development involves writing code that interacts directly with the hardware, such as initializing the processor, managing interrupts and exceptions, and controlling device drivers. RISC-V assembly language allows developers to have fine-grained control over these low-level operations, making it an ideal choice for OS development. Bootstrapping the operating system. The first step in operating system development is the bootstrapping process. Bootstrapping refers to the process of loading the initial code into memory and starting the execution of the operating system. This process involves several stages, including power-on self-test, post-bootloader execution, and kernel initialization. In RISC-V assembly, the bootloader is responsible for loading the operating system kernel into memory and transferring control to it. The bootloader code is typically written in assembly language and resides in a specific location in memory, such as the reset vector address. Kernel initialization. Once the bootloader transfers control to the operating system kernel, the kernel initialization process begins. During this phase, the kernel sets up the necessary data structures, initializes the hardware, and prepares the system for user applications. The kernel initialization code is responsible for configuring the processor, enabling memory management, initializing device drivers, and setting up interrupt and exception handlers. RISC-V assembly language provides the necessary instructions and mechanisms to perform these tasks efficiently. Process management. One of the primary functions of an operating system is process management. Process management involves creating, scheduling, and terminating processes, as well as managing their execution and resources. In RISC-V assembly, process management is implemented through a combination of context switching, scheduling algorithms, and system calls. Context switching involves saving the state of the current process and restoring the state of a new process. Scheduling algorithms determine the order in which processes are executed, ensuring fairness and efficiency. Memory management. Memory management is another critical aspect of operating system development. It involves managing the allocation and deallocation of memory resources, as well as protecting processes from accessing unauthorized memory regions. RISC-V assembly provides instructions and mechanisms for memory management, such as page tables, virtual memory, and memory protection. These features allow the operating system to efficiently allocate memory to processes, isolate their memory spaces, and protect against unauthorized access. Device management. Operating systems need to manage various input and output devices, such as keyboards, displays, disks, and network interfaces. Device management involves initializing and controlling these devices, as well as providing a unified interface for user applications to interact with them. RISC-V assembly language allows developers to write device drivers, which are software components responsible for managing specific devices. Device drivers communicate with the hardware through device registers and provide higher-level abstractions for user applications. File system management. File system management is the process of organizing and controlling access to files and directories on storage devices. Operating systems provide file system services to enable users and applications to create, read, write, and delete files. RISC-V assembly language can be used to implement file system drivers, which are responsible for interacting with storage devices and providing file system services. File system drivers handle tasks such as disk I/O, file allocation, directory management, and file access control. Conclusion. Operating system development using RISC-V assembly language requires a deep understanding of computer architecture and low-level programming. By leveraging the simplicity and modularity of RISC-V assembly, developers can implement the essential functions of an operating system, such as process management, memory management, device management, and file system management. Operating system development is a vast and complex field, and this section only scratches the surface of what can be achieved with RISC-V assembly. However, armed with the knowledge gained from this book, readers will have a solid foundation to explore and dive deeper into the fascinating world of operating system development using RISC-V assembly language. 12.3 Device drivers and hardware interfacing. Device drivers play a crucial role in enabling communication between software and hardware in a computer system. In the context of RISC-V assembly programming, device drivers are essential for interacting with various peripherals and external devices. This section will explore the fundamentals of device drivers and hardware interfacing in the RISC-V architecture. Understanding device drivers. A device driver is a software component that acts as an intermediary between the operating system and a hardware device. It provides an interface for the operating system to communicate with the hardware, allowing the system to control and utilize the device's functionalities. Device drivers are typically written in low-level programming languages like assembly or C to ensure efficient and direct access to the hardware. In RISC-V assembly, device drivers are responsible for managing the communication and control of peripherals such as keyboards, mice, displays, network interfaces, and storage devices. These drivers enable the operating system and applications to interact with the hardware devices by providing a set of functions or system calls that abstract the underlying hardware complexities. Hardware interfacing in RISC-V assembly. Hardware interfacing involves establishing communication between the RISC-V processor and the external hardware devices. This process requires an understanding of the device's specifications, including its registers, memory-mapped I/O, and interrupt handling mechanisms. Let's explore some key aspects of hardware interfacing in RISC-V assembly. Register access. Device drivers often need to access and manipulate the device's registers to configure its behavior and retrieve data. In RISC-V assembly, this is achieved by using load and store instructions to read from and write to specific memory addresses corresponding to the device's registers. By understanding the device's register layout and their functionalities, the driver can control the device effectively. Memory-mapped I/O. Memory-mapped I/O is a technique used to access peripheral devices by mapping their control and data registers into the processor's memory address space. In RISC-V assembly, memory-mapped I/O allows device drivers to interact with peripherals as if they were accessing regular memory locations. By reading from and writing to these memory-mapped addresses, the driver can send commands and retrieve data from the device. Interrupt handling. Interrupts are crucial for handling asynchronous events generated by hardware devices. In RISC-V assembly, device drivers need to implement interrupt handlers to respond to these events promptly. Interrupt handlers are routines that are executed when an interrupt occurs, allowing the driver to handle the interrupt and perform the necessary actions, such as reading data from a device or updating its status. To handle interrupts in RISC-V assembly, the driver needs to configure the interrupt controller and set up the interrupt vector table. The interrupt controller manages the interrupt signals from various devices and prioritizes them. The interrupt vector table contains the addresses of the interrupt handlers, allowing the processor to jump to the appropriate handler when an interrupt occurs. Writing device drivers in RISC-V assembly. Writing device drivers in RISC-V assembly requires a deep understanding of both the hardware device and the RISC-V architecture. Here are some general steps involved in developing a device driver. Device initialization. The driver initializes the device by configuring its registers and setting up any necessary data structures. Device control. The driver provides functions or system calls that allow the operating system or applications to control the device's behavior. These functions typically involve writing specific values to the device's registers to perform actions such as enabling or disabling features, setting parameters, or initiating data transfers. Data transfer. Device drivers facilitate the transfer of data between the device and the system memory. This involves reading data from the device's registers or memory-mapped I/O locations and writing data to the device for output operations. Interrupt handling. The driver implements interrupt handlers to respond to asynchronous events generated by the device. When an interrupt occurs, the handler is executed, allowing the driver to handle the event and perform the necessary actions. Error handling. Device drivers should handle any errors or exceptional conditions that may occur during device operation. This includes checking for error flags in the device's status registers and taking appropriate actions to recover from errors or notify the operating system. Cleanup and shutdown. When the device is no longer needed, the driver should release any allocated resources, restore the device to a known state, and perform any necessary cleanup operations. Conclusion. Device drivers and hardware interfacing are essential aspects of RISC-V assembly programming. Understanding how to write device drivers enables developers to interact with various peripherals and external devices efficiently. By leveraging the low-level capabilities of RISC-V assembly, developers can create robust and efficient drivers that enable seamless communication between software and hardware in RISC-V-based systems. 12.4 Application Development and Optimization. In this section, we will explore the process of developing and optimizing applications using RISC-V assembly language. As an assembly language programmer, it is important to understand how to write efficient and optimized code to ensure that your applications run smoothly and perform well on RISC-V processors. Understanding application development. Application development involves the creation of software programs that perform specific tasks or provide certain functionalities. In the context of RISC-V assembly, application development refers to writing programs using assembly language instructions to achieve desired outcomes. When developing applications in RISC-V assembly, it is crucial to have a clear understanding of the problem you are trying to solve and the requirements of the application. This will help you determine the appropriate algorithms and data structures to use in your code. Optimizing RISC-V assembly code. Optimization is the process of improving the performance and efficiency of code. In the context of RISC-V assembly, optimization involves making changes to the code to reduce execution time, minimize memory usage, and improve overall efficiency. Here are some techniques you can use to optimize your RISC-V assembly code. 1. Algorithmic optimization. One of the most effective ways to optimize your code is to improve the underlying algorithms. By choosing efficient algorithms and data structures, you can significantly improve the performance of your application. Consider using algorithms with lower time complexity and reducing unnecessary computations. 2. Loop optimization. Loops are a common construct in programming, and optimizing them can have a significant impact on performance. Techniques such as loop unrolling, loop fusion, and loop interchange can help reduce loop overhead and improve cache utilization. 3. Register allocation. Efficient use of registers is crucial for optimizing RISC-V assembly code. By minimizing the number of memory accesses and maximizing the use of registers, you can reduce the overall execution time of your application. Use the available registers wisely and avoid unnecessary register spills and reloads. 4. Instruction scheduling. RISC-V processors have pipelines that can execute multiple instructions simultaneously. By reordering instructions to minimize pipeline stalls and dependencies, you can improve the overall throughput of your code. Consider using techniques such as instruction reordering and software pipelining. 5. Memory access optimization. Memory access can be a significant bottleneck in performance. Minimize the number of memory accesses by using techniques such as loop blocking, data prefetching, and cache optimization. Consider using the appropriate data structures and access patterns to improve cache locality. 6. Compiler optimization. Modern compilers can perform various optimizations automatically. Use compiler flags and directives to enable optimization features such as loop unrolling, function inlining, and constant propagation. Experiment with different optimization levels to find the best balance between code size and performance. Testing and profiling. Once you have developed and optimized your RISC-V assembly code, it is essential to thoroughly test and profile your application. Testing helps ensure that your code functions correctly and produces the expected results. Profiling, on the other hand, helps identify performance bottlenecks and areas for further optimization. Use test cases that cover a wide range of scenarios and inputs to validate the correctness of your code. Consider using automated testing frameworks and tools to streamline the testing process. Profiling tools can provide valuable insights into the performance characteristics of your application. Identify hotspots in your code where most of the execution time is spent and focus your optimization efforts on those areas. Use profiling data to guide your optimization decisions and measure the impact of your changes. Conclusion. In this section, we explored the process of developing and optimizing applications using RISC-V assembly language. We discussed various techniques for optimizing code, including algorithmic optimization, loop optimization, register allocation, instruction scheduling, memory access optimization, and compiler optimization. We also emphasized the importance of testing and profiling to ensure the correctness and performance of your code. By applying these techniques and best practices, you can create efficient and high-performing applications in RISC-V assembly.